you very much. Um, okay, so all right. So this talk will be about new physics, in particular dark matter. But I thought that since we will be talking about new physics, I would start with some old physics. So back in the beginning of the 20th century, I guess, the then new physics were the electroweak interactions. People were trying to explain things like neutron decay. They did not know about the electroweak interactions, so they were writing down, as you all know, effective operators like 4 Fermi operators, which could explain the experimental data very well. However, there was a problem with these effective operators. If one would calculate the 2-to-2 scattering, for example, they would find that the cross-sections increase with energy. And comparing these cross-sections that would derive from the effective theory with the cross-section, an upper bound on the cross-sections implied by the so-called unitarity, and I will get back to that. They found that unitarity is violated when sufficiently high energies are reached. So the effective theory worked very well at low energies, but it broke down at high energies. This is because the parametric dependence of the calculated cross-section on the kinematic variables, the energy namely, is different than the parametric dependence of the upper limit implied by unitarity on the same variables. So we have one cross-section increasing with energy, the other one decreasing. They meet at some energy, and at this energy something new is happening. So this is how they figured out that they need to add something, and this something was, of course, the electroweak interactions. So for in many occasions, this and many others, unitarity has been the guiding principle or a guiding principle for theorists to decode new physics. It has been the thread that theorists have used to identify what new physics may be. And unitarity has been used very extensively also in recent times when people were working very passionately on LHC physics. But most of the times, unitarity has been employed in the high energy limit, so the relativistic regime.
Can you give another example?
I mean, the Higgs, the charm quark, I believe.
It was not. I mean, there was plenty of mistakes about it.
Okay.
No? I mean, people have had all sorts of ideas. But at the end, very few people were believing it was what it was.
You mean the Kapodistrian things? Okay, yeah.
No, what I'm trying to say is that I agree, but I interrupt you because, this is the only example of where it has worked really.
Isn't it also the charm quark was predicted?
No, it's a different mechanism. You need the Higgs in order to save the unitarity in the WW scattering to...
Right.
So it's a paper of Kapodistrian Cornwall about 70 something. So it was the first indication before even let me say the postulate of the Higgs that you need an extra scalar in order to save the unitarity.
Yeah. Okay. So. Now, if back in the beginning of the previous century, people could not explain neutron decay, today we cannot explain pretty much anything about our universe. So we know that our universe is full of energy components that are not made of the particles and the interactions we know. So this talk will be focused on dark matter. Okay, so the research in the past decades on dark matter came up with so-called canonical paradigm, the most widely studied dark matter scenario, which was that of electroweak scale WIMPs. So, and I would like to insist on the mass scale here that I've written up there. So, new particles coupled to the electroweak interactions with mass of around 100 GeV, so the mass of the weak gauge bosons. There were various reasons for which this kind of scenario was appealing, and I would like to very briefly summarize them. For one, these particles are assumed again to couple to the weak interactions of the standard model, so we do not need any new interactions. Then such particles do arise in many theories that were theoretically motivated, like supersymmetry, which aimed to address the so-called hierarchy problem of the electroweak scale and dominated the search for new physics in the past decades. On the phenomenological side, there were at least two independent motivations. One is the production mechanism of dark matter, because if we know one thing about dark matter is that it exists. So if it exists, we must explain how it was produced. And the reason we would like to explain that, or the reason we take this into account, is because identifying the production mechanism of dark matter, or ensuring that the production of dark matter is consistent with the observed density, is something that can guide experimental searches, can tell us something about the properties of dark matter, and then that can guide experimental searches beyond the dark matter density, obviously. WIMPs, because they couple to the weak interactions of the standard model, they are expected to have come in thermal equilibrium with the primordial plasma in the early universe, and so they acquire some abundance, and their final abundance is determined by the so-called freeze-out, which most people have heard here, so I will not explain. The result of the calculation of this thermal freeze-out is that the observed density is inversely proportional to the annihilation cross-section of dark matter. The more they annihilate, the more they stay in equilibrium, so the fewer particles we have left today. And we get the correct density if the annihilation cross-section times relative velocities of the order of a picobar, which is indeed of the order of the weak interactions of the standard model, and this is why this was called the WIMP miracle. And the other phenomenological reason is that this kind of scenario implements very well the canonical paradigm for structural formation, which is not a particle physics scenario. And this canonical paradigm for structural formation wanted dark matter to be collisionless and cold. Cold means that the dark matter particles became non-relativistic quite early on, and this allowed them to cluster very efficiently, because if particles have large velocities, they stream out of potential wells, and they do not cluster. If, on the other hand, they are cold, they can fall into potential wells and cluster efficiently. The other feature is collisionless. Collisionless means two things. One is that particles decouple from radiation quite early on in the early universe, so they are not kicked around by radiation, and this again allows them to start clustering sufficiently early in the early universe. Collisionless also means that particles do not interact, dark matter particles do not interact inside halos today. And turns out that if particles do interact significantly inside halos today, that can affect gravitational structure. Okay, so the collisionless cold dark matter paradigm has been very successful in explaining observations, how matter clusters and forms the galaxies that we see, at least at large scales. So for all of these reasons, WIMPs, electroweak scale WIMPs, were put on the pedestal of BSM physics. However, much like all empires, the time came for WIMPs to be dethroned. And there are reasons for which they were dethroned. So let me walk this backwards, starting from structural formation. It turns out that the collisionless cold dark matter paradigm reproduces the large-scale structure of the universe very well at large scales, meaning larger than a megaparsec. And just to give you an idea, a megaparsec is roughly the distance between two large galaxies. But it turns out that at smaller scales, subgalactic scales, or small galaxy scales, so dwarf galaxies are things like Ursa Minor and Major that we see in the sky at night. So at small scales, it turns out that collisionless cold dark matter predictions present some discrepancies with observations. In particular, as I said before, collisionless cold dark matter clusters way too efficiently. And observations suggest that gravitational clustering is not as efficient as collisionless cold dark matter predicts. And of course, this can be made precise. It is not just words. Okay, so one possible resolution to this issue is that dark matter is actually maybe not cold or not collisionless. But the most promising avenue is to consider non-collisionless dark matter, so which we will call self-interacting dark matter that has some significant self-interactions. It turns out that in order to satisfy this requirement, together with constraints that exist on dark matter self-interactions, upper limits that exist, the particle physics scenario class of models that can do that is when dark matter has long-range interaction, it couples to light force mediators. So here we first we see that we introduce a hierarchy between the dark matter mass and the mass of the mediators, the force mediators to which it couples. So let's keep this in mind and move on. Let's go back to the freeze out, to the WIMP miracle, the glorious WIMP miracle. It turns out, if you do the calculation carefully, in fact, the mass of the WIMPs that you need to produce the correct dark matter density has to be in the TeV scale, not the electroweak scale. Naturally, WIMPs live, WIMP miracle WIMPs live in the multi-TeV scale. The details, of course, the exact result depends on the details, what multiplets you consider, and this and that. But the saddest of all things is that despite our best efforts, we actually have failed to discover electroweak scale WIMPs. This gives motivation, of course, to look for physics, to consider physics at higher scales. So we have kind of covered the regime up to TeV in some ways. So this motivates looking in the multi-TeV range. So motivated by all this, what I would like to talk about is two different directions to look beyond weak scale WIMPs. One is heavy thermorelic dark matter, so basically continue doing what we have been doing all along. So consider thermorelic dark matter in the multi-TeV regime, and also consider self-interacting dark matter. So I do not have a specific agenda here. I'm not trying to convince you about a specific dark matter candidate. What I am trying to present is new dynamics that emerge when we extend our searches in well-motivated directions for dark matter. Now, the way I will talk about these two topics, or the common thread that I will use to talk about these two topics, will be unitarity. But now unitarity in the non-relativistic regime. Why non-relativistic? Because most of dark matter phenomenology, including its production in the early universe, happens in the non-relativistic regime. Okay, so as I hinted already, or I'm not sure if I said it clearly. Again, the unitarity will be the common thread, and the topic I will talk about, the new dynamics that emerge, is the dynamics of long-range interactions. So let me start by defining what do I mean by long-range interactions. Well, an interaction manifests as long-ranged if the range of the interaction, which is the inverse mediator mass, is longer than the de Broglie wavelength of the interacting particles, so 1 over the momentum. But it turns out there is another scale that is important, which is the Bohr radius, or the Bohr momentum, where we replace the velocity of the interacting particles with a coupling, well defined within specific theories. So in a QED-like theory, this alpha over there is the fine structural constant. And now it is very easy to do a calculation for the electroweak interactions, first of all, which we know. You can plug in the electroweak, the weak coupling, and the mass of the W and Z boson, and you will find that even the weak interactions of the standard model, which have been the prototype of contact interactions in particle physics, even the weak interactions manifest as long-ranged if the mass of the interacting particles is heavier than a few TeV. Yeah? And of course, beyond that, if we consider different theories, there is a much larger range of applicability of long-range interactions. Now, what happens if the interactions manifest as long-ranged? There are two main effects that affect any phenomenological calculation and consideration. The first one is the Sommerfeld effect, which is the fact that the wave function of the interacting particles is affected by the long-range interaction. The wave function is not a plane wave anymore, and this means that the cross-sections for any process in which the interacting particles participate change. And they change in important ways that, of course, affect phenomenological predictions. This is the Sommerfeld effect. But in fact, The Sommerfeld effect, despite the fact that this is the first thing one encounters when one considers longer-range interactions, is only the tip of the iceberg. There is a much more important and rich effect that occurs, and this is the fact that long-range interactions typically allow for the existence of bound states. If bound states exist, they will form, most likely, and if they form, they can dramatically change the phenomenology of dark matter today. We know this from ordinary matter because ordinary matter has all sorts of long-range interactions and it forms all sorts of bound states, and astrophysics would be very different today if these bound states had not formed. For one, we would not exist if hydrogen atoms had not formed in the early universe. Okay, so there are different types of bound states. I have noted here two categories: metastable bound states and stable bound states. Metastable bound states have the feature that if they form, then they decay into radiation, and that opens up a new annihilation channel of dark matter. Remember, the annihilation of dark matter is a very important effect to calculate the relic density and all sorts of other signatures of dark matter. Now, the stable bound states can, as I mentioned already, if they exist and they form, then they change the phenomenology of dark matter much more dramatically. So the metastable ones are, a subtle effect. Turns out it's not subtle at all. Okay, so let me now talk about these things in the context of the first scenario, heavy thermorelic dark matter, the production and indirect detection. So we can start asking the question, how heavy can thermorelic dark matter be? The defining characteristic of thermorelic dark matter is, as we already mentioned, the annihilation cross-section. In order for dark matter to thermalize in the real universe and then acquire the correct abundance, we need this so-called canonical annihilation cross-section, which is, as we said, of the order of the weak interactions. But, okay. Now, cross-sections. What is a cross-section? A cross-section is, roughly speaking, phase space times probability for scattering. And unitarity is this sacred principle in particle physics or in quantum mechanics that tells us that things have to add up to 1. The probability for scattering cannot exceed 1. So if one of the factors there cannot exceed 1, then that gives us an upper limit, an upper bound on how large cross-sections can be. This upper bound applies on partial wave cross-sections. It will not depend on the parameters that determine the strength of the interaction. So, of course, it will not depend on any couplings, but it depends on the remaining part that affects the cross-sections, which is phase space. So it will depend on phase space variables. It turns out, quite crucially for our discussion today, that this dependence on the phase space variables is not 1 over the energy, but it is 1 over the momentum squared. So the upper limit on the cross-sections goes as 1 over the momentum squared, and the momentum is the energy in the relativistic regime, but it's something very different in the non-relativistic regime, and because it is different, that gives us the possibility to ask and answer very interesting questions. So now we know that thermorelic dark matter requires some annihilation cross-section. We know that annihilation cross-sections are bounded by unitarity. We can put the two together, and this is what Grist and Kamiankovsky did back in the 90s, and they said, well, this implies an upper bound on the mass of thermorelic dark matter, which if you plug today's values of the relic density, this is of the order of 100 TeV. So we have a limit for our experimental searches. Importantly, this argument relies on the fact that on the argument that the lowest partial wave dominates, the S wave, and they had a reason to claim that this is so. We will question this argument. Okay, so now, but in the process of questioning this, we can ask a more important question than how heavy can thermorelic dark matter be, and we can actually ask what is the underlying physics that can realize the unitarity limit. From a phenomenological perspective, if you care about thermorelic dark matter at the 100 TeV scale, then you must have a theory that gives you a cross-section that is as large as the unitarity limit allows. And so the question is, what kind of theory can give you cross-sections as large as the unitarity limit allows in the non-relativistic regime. So instead of asking what is the physics of thermodynamic dark matter, we will first of all ask what is the physics underlying the unitarity limit in the non-relativistic regime. And the way we will answer this question is the way people answered this question in the past, by looking at the dependence of the unitarity cross-section on the kinematic variables.
Let me ask a question, Kaya. To reach this conclusion about the unitarity limit, I suppose that you have to assume the content of the theory in terms of field of particles, right?
No, about the cross-section or the dark matter mass?
Well, I don't know. When you reach this conclusion, you assume a certain spectrum that you have, right? But I suppose that if I double the number of fields that I have in the theory, which we don't know, because we don't know what that matter is made of, this could affect or not the unitarity.
No. So you're asking about the bound on the dark matter mass?
Yeah.
Okay. No, I mean, you assume that dark matter consists of one species. Let's say that. It's the lightest of all species that are charged under a symmetry that stabilizes dark matter, usually, like R parity in supersymmetric models. It has to be stable. And then that's all you care about.
And if instead of one I have a triplet, it won't change the unitarity bound.
If you mean you have a broken, like the electroweak triplet, you mean? Well, after the electroweak phase transition, there is a mass splitting between the components of the triplet, and dark matter is the lightest of all components. Yeah. Okay. So now we want to answer the question: what physics can realize the unitarity bound on the cross sections? And the first thing we can do is check with our beloved contact type interactions that people have been studying in the context of dark matter and phenomenology and BSM physics in general for many years. So if you assume that dark matter interacts via a mediator that is heavier than itself or of the same or has mass of the same order, which is the case for weak scale WIMPs, so 100 GeV dark matter, 100 GeV mediators, they're roughly the same scale, the interactions are contact type, then what you get is an annihilation cross-section times the relative velocity that has this parametric dependence. So it scales as 1 over the 4th power of the mediator. It is proportional to the energy of the collision, which is the dark matter mass, and has some coupling over there. And depending on the partial wave, you get some velocity suppression. Okay, now compare this cross-section with the unitarity limit, and what you will see is that unitarity is violated if the dark matter mass is sufficiently heavy. So again, what you see here is a hierarchy between scales. Now, just a brief comment, these are renormalizable parameters. They are not allowed to be constrained by unitarity. They are allowed to be whatever they like. So the fact that unitarity is violated when this inequality holds means that we have forgotten something in our calculation. Now, quite importantly, how are we going to find this something? Well, we will find this something by staring carefully at the condition that we get from the violation of unitarity. And what you see here is, again, the comparison between two scales. It is not simply the mediator mass and the dark matter mass, but this is multiplied by some combination of couplings and velocity. This reminds us the condition that I wrote earlier about the interactions manifesting as long-ranged. And indeed, if you think about it more carefully, and some people did very long time ago already, it turns out that what you are missing here, the physics that has not been included here, and the physics that will restore unitarity, is the physics of long-range interactions. What happens here is that when this inequality is true, the interactions manifest as long-ranged. Let us go check this statement. If we now consider a long-range interaction, so say you have QD, and you calculate the plus and minus annihilation into 2 photons, or equivalently dark matter annihilation into whatever force mediators you have. But now, the dark matter will be heavier than the mediators. So at 3 level, you get an annihilation cross-section that looks like this. It scales as 1 over the dark matter mass squared, not as 1 over the mediator mass to some power. And then there is this factor, the so-called Sommerfeld enhancement factor, which is the fact which arises from the fact that the wave function of the interacting particles is distorted because of the long-range interaction. And if you go to the regime where the velocity is quite low or the coupling is sufficiently large, what you find is this expression that I have written over here. And now let's play the same game. Compare this cross-section with the unitarity limit. What you will see is that this cross-section has exactly the same parametric dependence on the kinematic variables, the momentum, namely, as the unitarity limit. And in fact, this holds for all partial waves. And so again, now, if you compare these two cross-sections, what you will find is that unitarity is violated at some point. What point? Well, if the coupling becomes large enough. But this is very different than the unitarity violation we saw before, which was a comparison between 2 different scales. And when we have a comparison between 2 different scales in physics, we know some new physics is going on. This is a failure of the perturbation theory. It is the fact that the coupling has become large enough, and now we have to restore unitarity, include terms in the perturbation expansion that we had neglected before. Okay, so what this story tells us is that the unitarity limit on the cross-sections, and therefore the unitarity limit on the mass of thermoelectric dark matter, the unitarity limit on the cross-sections can be realized in a continuum of momenta in the non-relativistic regime only if the interactions manifest as long-ranged. And if the interactions for the unitarity limit if the interactions manifest as long-ranged, when we want to approach the unitarity limit, then this means that thermoelectric dark matter in the 100 TeV regime has long-range interactions. And if this is true at 100 TeV, chances are it is true also at lower masses. And in fact, in explicit scenarios, explicit calculations in specific scenarios of thermoelectric dark matter, this behavior appears already at a few TeV, much like for weak dark matter coupled to the weak interactions. Okay, so we learned that in variable thermoelectric dark matter models in the multi-TeV regime, the interactions manifest as long-ranged. The annihilation seems to still be dominated, well, it has this interesting velocity dependence, which is important for phenomenology, but it still seems to be dominated by the lower partial waves. And that would be it, and then we would still have this upper limit on the mass of thermoelectric dark matter. And that would be it if there was not a coup de théâtre, if we didn't have a new twist, which is the fact that long-range interactions imply the existence of bound states. And why is this interesting and relevant here? It is relevant because metastable bound states can form and decay into radiation, and in that way, as I already mentioned, they open up a new annihilation channel for dark matter. To convince you that this is important, here is the cross-sections versus alpha over v, so inverse velocity, annihilation and bound state formation for a dark QED model where we have dark fermions coupled to a massless dark photon. And what you see is that at large velocities, the annihilation dominates, but in the regime where the Sommerfeld effect becomes important, so when alpha over v becomes larger than 1, bound state formation is actually the dominant inelastic process. And here in this simple model QED, it's a difference of only a factor of a few. But in fact, if you go to non-abelian models, the difference can be orders of magnitude, which means that we should redo all of our calculations. This is a complete overhaul of the thermoelectric scenario in the multi-TeV scale. Now, importantly, what happens is that, so you can see it already in this simple model, the annihilation, the dominant contribution is S wave, but the dominant bound state formation process is actually P wave. And both of them have the same velocity dependence at low velocities. And so this means, and this can be argued in more specific ways, in more general ways, not specific, that higher partial waves become important. Now, if we go back and remember the unitarity limit on inelastic cross sections, it increases with partial wave. Now, if higher partial waves become important, this means there is no upper bound on the mass of thermorelic dark matter. The reason that higher partial waves become important for bound state formation and not for annihilation contains physics itself. And I would like to explain this physics because I find it very interesting. What is happening here is, so this is the form of an annihilation cross-section before we include the Sommerfeld effect. And you see that's suppressed by v to the power of 2L, the velocity at the power of 2 times the partial wave. This is if we do not include the long-range effects. When we include the long-range effects, we said that the long-range interaction distorts the wave function. So the wave function is not a plane wave anymore. If it is not a plane wave, the momentum is not fixed. It contains an uncertainty. What is this uncertainty? Well, this uncertainty must scale with the coupling because the coupling is what creates the issue, right? So the Sommerfeld effect is something that becomes important when the quantum uncertainty in the momentum becomes larger than the classical value. When alpha becomes larger than v, alpha is the quantum uncertainty in the velocity, v is the classical value. And so what you see here is that alpha replaces v. What you see here when you include the Sommerfeld factor is that the quantum uncertainty replaces the classical value. And what happens is, so we get rid of the velocity suppression. However, the suppression doesn't go away. It becomes a coupling suppression. And so annihilation cross-sections of higher partial waves are still suppressed. This is not the case for bound state formation, and the reason is quite technical. I will not fully explain it, but you can see diagrammatically here. The reason is these ladder diagrams, which represent the bound states in the final state. And these ladder diagrams are non-perturbative because they scale as 1 over powers of the coupling. So the order of these diagrams is actually lower than what you would expect naively by perturbative considerations. And this is what makes higher partial waves important. How much time do I have? Oh, okay. Okay. All right. So, okay. Now, so we already saw how bound states can severely affect. Well, I didn't show results of freeze out, but you will believe me. Bound state formation and decay can severely affect the Rayleigh density of dark matter. But of course, they can do more things. In particular, they can contribute to the indirect detection signals of dark matter. In fact, bound states, basically, what we're seeing here is the emergence of a new type of inelasticity. And this inelasticity affects production and detection signals of dark matter. So if bound states exist, they will form, as we already discussed, and metastable bound states will decay into high energy radiation, which will simply enhance the annihilation signals of dark matter with high energy, high energy radiation. But another thing that is happening is, in order for bound states to form, this is a transition from higher energy states to lower energy states. Invariably, it has to happen with dissipation of energy, and this energy is a small amount of energy, is of the order of the binding energy, much lower than the dark matter mass. So what we see here is that the formation of bound states actually produces low energy radiative signals. This is a novel signature that did not exist when we were considering simply contact type interactions for dark matter. And quite interestingly, it exists both for the formation of metastable bound states that then decay and produce also high energy signals, but also for the formation of stable bound states, like, say, dark hydrogen atoms, which would form with the emission of a dark photon. This gives the possibility to probe a different class of models, the so-called asymmetric dark matter models, which do not have any annihilation signals. Okay, so again, there is a whole host of phenomenological implications because of that. Just to summarize on the issue of heavy thermoelectric dark matter, what we learned is, first of all, that the only thing that is not true is that there is an upper bound on the mass of thermoelectric dark matter, but we learned something much more important. We learned what the underlying physics of heavy thermoelectric dark matter can be, and we got an idea about what the experimental signatures may be and how they may change. And in particular, the indirect detection signatures, there are novel signals, as well as the fact that the momentum dependence of the cross-sections implies that changes the strength of the signals, and in particular implies that the substructure inside halos can be very important, because the substructure means not only higher density, but also lower velocities, which give you extra enhanced signals when you have long-range interactions. So there is a lot of work on that, but let me move on. Now, this is not the only thing that unitarity can do for us. Yes?
Knowledge about the physics that you are presenting things in the sky?
We may have misinterpreted things on the sky, but the first, when you're looking for radiation in the sky, the first thing you have to do is and the hardest part is to distinguish backgrounds from signal, and that does not have much to do with the underlying physics. Then once you are confident that you have a signal, which people have been confident several times, then it's a matter of interpretation, and then the underlying physics is important, and all of this has been invoked in various contexts in the past and will be invoked in the future. Okay, so let's go back to unitarity, because unitarity is a very rich topic and can tell us even more things. So we said that unitarity is the principle that probabilities have to add up to 1, but a particle or a pair of particles that interacts can interact in many ways. It can interact inelastically, but also elastically. So unitarity, in fact, does not put an upper limit on just inelastic cross-sections, but it puts coupled constraints on elastic and inelastic cross-sections. So here you see the full deal. This comes simply from the partial wave analyzing the optical theorem. Okay, so the unitarity cross-section again is this thing over here. And plots are better than equations sometimes. So what you see here is this upper limit on the inelastic cross-section, which depends on the elastic one. Okay, so this equation is this equation, elastic on the horizontal axis, inelastic on the vertical axis, and there is a mapping between this plot and the unitarity circle that you see over there. Okay, now I would like to flip this diagram and now look at this from the point of view of elastic interactions rather than inelastic. So here is the flipped diagram, and what you see is that there are constraints on the partial wave elastic cross-sections, and these constraints change depending on the inelasticity. Inelasticity makes the upper bound on the elastic cross-sections more stringent. This is because if inelastic cross-sections are very important, they remove particles from the flux. If you think about it as a scattering experiment, beams colliding, you remove particles from the flux because of the inelastic interactions, and so this leaves fewer particles to interact. So this puts a more stringent upper bound on the elastic cross-sections as the inelastic cross-section increases. But, quite interestingly, there is also a lower limit implied by inelasticity on elastic cross-sections. This is because if particles interact inelastically, they can do that twice. They can produce some new particles via the inelastic interaction. These particles can interact back and give the original particles. So inelasticity contributes to elasticity. Yeah? Why is this important phenomenologically? Because I'm a phenomenologist. It is important in the context of what we said before because of self-interacting dark matter, which cares about how large the elastic cross-section of dark matter is. Now, I already talked about this and I don't have very much time, so this is the motivation or the issues of collisionless cold dark matter. Self-interacting dark matter is one solution. So, to these discrepancies, observational discrepancies, now, what do we exactly need? So it turns out that in order to affect structure at small scales, we need an elastic cross-section per dark matter mass of the order of barn per GeV. By the way, this is quite large. This is of the order of the nuclear cross-sections. This is why barn is called a barn. But turns out there are constraints from large-scale structure, things like the bullet cluster that you see here in the background, which are of the same order. So how can we reconcile the two? How can we have a large cross-section and then also bound it at the same time? Well, we have to remember that cross-sections depend on energy. And here is where the job of particle physicists comes in. We need to affect structure at small scales, small galaxies, which are characterized by low velocities of the order of tens of kilometers per second, while the constraints we have on the self-interactions come from large structures, like the bullet cluster, that are characterized by large velocities of the order of thousands of kilometers per second. And so the way to reconcile the two is in fact have an interaction that is long-ranged. Why? Because long-range interactions scale inversely proportionally to some power of the velocity. So if you consider, for example, Rutherford scattering, it scales as 1 over the velocity to the 4th power. And that makes the cross-sections at these two scales extremely different. Okay, but now this is the very rough picture. So let us go examine what is happening. While still remaining in the rough picture, what people usually do when they study self-interacting dark matter is they say, well, okay, we have a light force mediator, so dark matter interacts, dark matter particles interact with each other via Yukawa potential. Here's a Yukawa potential. It has, well, 3 parameters, the coupling, the mediator mass, and the dark matter mass. And you plug this into Schrödinger's equation, you find the elastic cross-sections. Because you have a mediator mass, these present some parametric resonances that have something to do with the thresholds for the existence of bound states and this and that. So here what you see is cross-sections versus velocities for various values of the parameters. So then they consider things like this, and they do their phenomenological study. This would all be very good, except we know that when there are long-range interactions, there is very significant inelasticity. And inelasticity can change the situation very dramatically. It can change the situation when inelastic interactions are real. And again, we know this from the physics of ordinary matter. So when we say inelastic interactions, first of all, we mean things like Bremsstrahlung, which dissipates energy and makes halos collapse into disks. We mean also for particle physicists things like annihilation or bound state formation that I mentioned before. So if inelastic interactions do occur for real, then they can change the state in which dark matter is, and that can change everything. So 2 ions collide in very different ways than 2 hydrogen atoms, right? So if this is happening in a dark sector, if dark sector has similar physics as QED, and dark matter is asymmetric, so we have particles and not antiparticles, and dark atoms form, that is very different from having just ions, right? So this is just one example. There are many more examples, but this is to convince you again, real inelastic interactions dramatically change the situation, dramatically change the state of dark matter. What I would like to talk about, though, in the remaining couple of minutes, is a much more subtle effect that goes very much in the core of quantum field theory, and this is the fact that as I mentioned before, inelasticity feeds into elasticity virtually. So in other words, we have E plus E minus going into gamma gamma, going back to E plus E minus. So contributing diagrams like this to the self-energy of an E plus E minus pair. Or more importantly, E plus E minus forming a positronium-like bound state with emission of a photon and going back to E plus E minus. So diagrams of this type. Now you can say, obviously, this is very unimportant. Loop suppressed, coupling suppressed, who cares about all of this? And that is true, except if the interactions that go into here are actually close to the unitarity limit. And this brings us back to the coupled constraints between imposed by unitarity on elastic and inelastic cross-sections. To satisfy the when we talked only about inelasticity, inelastic cross-sections, to satisfy these constraints, to be in agreement with unitarity, we had to sum the purely elastic interactions like one boson exchange. And this gives us typically a Hermitian potential. But in fact, to satisfy the whole thing, well, what you need is to also resum the inelastic processes, the contribution of inelastic processes to the self-energy of a state. And this gives an anti-Hermitian potential. So, again, you expect all of this to be super suppressed unless the inelastic interactions you resum, are actually close to the unitarity limit. And what interactions are close to the unitarity limits? Inelastic interactions? Well, long-range interactions. Okay, so we did that in some recent work. We did a complete resummation in the non-relativistic regime, so the result does contain non-relativistic approximations of the anti-Hermitian kernel that arises from inelastic interactions. And we managed to produce some formulas which surprised us ourselves by their simplicity. So here what we have is the unregulated cross-sections, which include only the Hermitian potential that can come from interactions like one boson exchange, purely elastic interactions, and the regulated cross-sections, which include the resummation of inelastic processes, squared, doubled, right? And so here are the corrected cross-sections versus the uncorrected ones. And indeed, you see the formulas are surprisingly simple. What you see is that, first of all, there is this regularizing factor, which depends on the unregulated inelastic cross-section. And again, this tells you that if inelasticity is significant, you remove particles from the flux, so you suppress the cross-sections. So the inelastic cross-section is corrected in this very simple manner. The elastic cross-section is more interesting because, yes, it is suppressed by this same factor, but then there is another component which corresponds to the regeneration of the flux due to inelastic interactions squared. So plots are better than equations. So here is the plot, corrected cross-sections versus the uncorrected inelastic cross-section. You see the inelastic cross-section that increases, but its growth is tamed by this regularizing factor. And if the unregulated inelastic cross-sections are too large, you see actually the opposite effect. And then for the elastic cross-sections, depending on what you start out with, you can have, things can go both ways. Why is this important? This is important for, phenomenologically, for self-interacting dark matter. And this is some work in progress with my student in Paris. So I will conclude with this modest proposition, which is that, again, unitarity has been a sacred principle in particle physics. It has given us a lot of intuition throughout many decades. So my proposition is, let us use unitarity in a new context and in a new regime, the non-relativistic regime, where it has not been fully explored yet, to understand or to probe the plausible dynamics of the dark matter. Thank you.
Questions? Yes.
So, between the two scenarios that you mentioned, the thermal rate dark matter, did I understand correctly that this radiation is one of the main signals that it predicts, that it's also hard to test experimentally in this scenario, because precisely radiation is hard to tell which source it comes from.
This is an issue that plagues in direct detection in general. To distinguish backgrounds from signal, yes, I mean this is. In direct detection is a whole field that employs many people, right? So it has. I mean, I'm proposing here some new types of signals. Of course, it is difficult to distinguish them, much like the other signals are, but.
Yes, I do not understand if you have. These are very interesting ideas. Have you compared them with all
with observations, you mean?
Observations, yeah. And how do they?
Yeah. So yes, sorry, I didn't show plots because time was finite. But so, for example, we did an analysis for a dark U1 model. No. So and we found that you get, because of the high energy radiation you get from the bound state decay, you can get stronger constraints. Because you enhance the high energy signals, so you constrain more parameter space. So we did that for the context of for a dark U1 model. For the low energy signal from bound state formation, which is more novel, it is more difficult. We have done an analysis for that too, and we actually showed that you can explain the 511 kV line in the center of the galaxy with a massive dark photon emitted during bound state formation that then decays into a plus minus. But in general, that type of signal is harder to detect because it is low energy, but its rate is suppressed by the number density of dark matter. Dark matter is still heavy, so the number density is low, but then you have a low energy signal which has a larger background. So the interplay, it works against, it makes it more difficult. However, there are now new searches, like, for example, COSI, which will be looking and will have much larger sensitivity on MEV energy range, and can probe lines. And so these signals become more and more interesting, because if you get a line signal, it's actually more easier to detect than a spectrum. And if you have now more sensitive instruments that focus in the low energy regime, that opens up new prospects.
So you discussed some bounds or constraints. Do they exist in patterns of bounds or constraints? I don't know, from Big Bang synthesis or other processes or other. So do you exhaust those constraints or constraints?
There are many kinds of constraints. So there is direct detection, where you expect the dark matter particle to hit your detector in an underground lab inside the mine, right? And then produce a scintillation signal or something. There are constraints from that on the interaction cross-section between dark matter and neutrons. There are constraints from indirect detection on how dark matter can radiate. There are constraints from colliders, that whether you can. So these constraints, you have to. They are model dependent. So I did not very specifically discuss a specific model here, but they exist. So I'm not sure if.
Yeah, this interactive model that you described, basically all within class, they can't satisfy.
Are you asking about self-interacting dark matter in particular? Okay, so the simplest way you can think about self-interacting dark matter is that it resides in its own dark sector and produces no other signals. This is the simplest version of it. It's not necessarily the only version one should consider, or that we consider. Most of the times we don't. We consider other versions, and then constraints do apply. Yeah.
Other questions?
Is your analysis sensitive on the assumption that dark matter is one component? I mean, can you embed the whole thing into a multi-component dark matter picture?
I very much like multi-component dark matter. But I also like multi-component dark matter that arises dynamically, not by people just assuming that instead of having one dark matter component, you have 7 of them and no connection between them, right? So, in fact, one thing I find very interesting is that when you have long-range interactions, and typically asymmetric dark matter, you naturally get multi-component dark matter. And the simplest scenario of this type is when you have, again, a dark QED scenario with an asymmetry, particle and antiparticle asymmetry, which immediately tells you that because of dark charge neutrality, gauge invariance, you need to have two dark matter components, dark protons and dark electrons. And if dark protons and dark electrons exist, they will form dark hydrogen atoms. So you immediately get multi-component dark matter, even if you didn't ask for it. Yeah? And then the phenomenology is very rich. And it's actually, even in this simplest scenario you can think of, it's very hard to delineate the parameter space because all sorts of things can be happening. And what is happening does not only depend on the fundamental parameters, but it also depends on the thermodynamic environment that you consider. So when you talk about long-range interactions, many people immediately say, oh, you have a lot of dissipation, and so dark matter halos would not be triaxial, they would collapse on a disk like ordinary matter does. Well, no. Dissipation is actually a very hard effect to achieve. Efficient dissipation is very hard to achieve. It's not because you have a light mediator, you have dissipation, efficient dissipation. So the phenomenology becomes richer and very interesting, yeah, and naturally you get multi-component dark matter.
Last question.
Okay, very short. So if I understand correctly, so from the unitarity of the non-relativistic cross-section, you get a handle on the long-range interaction. Is it possible on the side, right? So is it possible to relax this if I have more, a more rich dark sector, or the fact that it comes from the non-relativistic limit makes it bulletproof essentially?
So you want to have again the framework we work here with is thermal relic dark matter, yeah. And so are you asking the question if I have many different species unrelated to each other that each one of them freezes out independently?
I'm more asking what the mediator, because it's clear that this scenario would be. So if you would have more mediators, a richer mediator spectrum, will you have different long-range interactions?
I mean, you can have many mediators, and in most models you do have many. So, for example, even in WIMPs, you have, first of all, there are several weak bosons, there are two, and then there is the Higgs also, in many, that couples to WIMPs in many models. But, I mean, again, if you want to reach the upper limit on the cross-section, which is what takes you at 100 TeV, that upper limit in the cross-section is reached only if you have long-range interactions. That's the thinking.
Okay, let's thank Kat again. Thank you very much for it. Okay. Okay, the next speaker is Emmanuel Stamo, and talk about CP and flavor violation as a prop for new phenomena.
Thank you very much for having me. So actually, even though I'm from Athens, it's my first time as a physicist in Athens. So I'm very happy that you invited me. And yeah, so I'm also an exotic in this room, like Kalia. So I'm a phenomenologist. So you will have to bear with me today. But if you ever invite me again, maybe next year, I can tell you about how a crossing symmetry is violated in Chen-Simon series.
The second, yeah, so next year is over.
I mean, you would, sure. Okay, but today I will stick to phenomenology, and I will try to be more schematic and give you a little bit of an idea of what's happening. So I will focus on CP and flavor violation. So as you know, so I will try to be very explicit. So CP is something that is violated in the standard model, but only over this CKM parameter of the CKM matrix that we have. And flavor is the number of different quarks that we have, or the number of different leptons that we have. And I will talk about how this type of effects can have an impact our understanding or our search for new phenomena, new physics, I will call it, okay? So, what is the status, or what's going to happen in the particle physics frontier, the experimental frontier in the next, decades, essentially? Well, what's going to happen is that we're going to still have LHC with its big experiments. It's going to collect a lot of data in the high luminosity phase. And at the same time, we're going to have a separate, that's relevant for my talk, separate experiments that are going to look for rare phenomena and potentially sensitive to new physics phenomena in the quark sector. There is going to be a big dump facility at CERN, the SHIP experiment, and there are also many different experiments that are very highly relevant for these searches for new physics, namely electric dipole moments, the G-2 experiments, Nagillo facilities, direct detection of dark matter, and also axion searches that I'm going to enter. So the point of the phenomenologies is to make sure that this huge amount of data maximize their impact. Okay, so we'll have to combine them in order to maximize and guide the future experimental program and gain as much possible out of them as we can. So what are the open questions? So that's nicely tied to the previous talk. So we have our different energy scales. So here I go to the right as the high energies. And there are some questions that we can ask as a low energy particle physicist. Okay? One of the questions that we can ask is whether the Higgs particle that we find is indeed the one that we think is in the standard model, right? So that goes back to the question that was raised before. So why do we need this Higgs? So this Higgs was one way to unitarize WW scattering, but there are many ways to unitarize WW scattering. So is this the one that we have in the standard model or not? Another question that we can ask, and it's going to be relevant for my talk, is that we have baryogenesis, so we have more baryons than antibaryons. So the question is, how do we get new CP violation? Because the CP violation that we do have in the standard model is not sufficient to provide a model for baryogenesis. Another question that we have is whether or to which extent we missed some degrees of freedom at any scale. So this could be particles that we're missing and we're not seeing because there are some compressed spectra associated electroweak. They can be very heavy and therefore we do not see them. But they can also be much lighter. For instance, there can be QCD axions that solve the strong CP problem. There can be dark matter, WIMPs, and so on. So, and maybe one of the questions that maybe you care more is what would be the next fundamental scale, all right? So could we have some new supersymmetric scale or some composite Higgs? So, however, even though it is clear that physics beyond the standard model must exist in some way or another, okay? So we need them for baryogenesis, we need to find a solution for dark matter. It doesn't have to be particle, but it could be. So we have multiple questions. We also have theoretical questions related to hierarchy problem, strong CP problem, and so on. However, what we must understand as a particle phenomenologist or particle physicist today is that it is not clear which type of beyond the standard model models we can actually access with the current or future experiments. So we're in an era of no guarantees, essentially. And this also implies what the key strategies are. Okay, so the key strategies are to ask data-driven questions that can be answered, okay, and try to provide model-independent interpretations as much as possible. And in order to maximize the impact, as a theoretician, we try to be as precise as possible to sort of distill out all these effects. So I will give two examples in my talk. So this will be the focus of my talk. So here is again my energy scale. So as we go down, we have low scales. So potentially, okay, so low scales below, high scales above. Above, I have put the electroweak scale, where we know that we have dynamical particles. We have the top quark, the Higgs, the W, and the Z. We have lower scales in which some of those experiments are very are probing. So they create a lot of B mesons, D mesons. These are sort of composite QCD resonances, and they try to understand the array processes. And there is even further down a lower scale in which potentially we can have new particles that we have not observed, Why have we not observed them? Because we have to assume that they interact very quickly with us if they exist. So be the QCD axion, dark photons, and so on. And I decided for this talk today to give you two examples. One in which we're looking for indirect signals of new physics by looking at the electroweak sector. I'm going to look at anomalous Higgs couplings, in particular CP violation in the Higgs sector, and relate them to electric dipole moments that live down here or here. And the next example I'm going to give, which is going to be similar in some way, is that I'm going to look at light new physics that interact with us very weakly and ask the question about how potential experiments here can give us some potential insight about their existence. So let me start with anomalous Higgs couplings and CP violation. So the Higgs, this is a very rough summary of what Atlas and CMS are telling us. So they tell us that the coupling is indeed as we expect in the standard model paradigm, okay? So it is proportional to the mass of the particle with which the Higgs couples, okay? However, there are very few points on this plot, okay? So this is the particle mass at which the Higgs couples, and this is the coupling, okay? And the standard model is such that you need to be on this line. So it's beautiful that we have points on this. It's also beautiful that the errors are small, but this is only a very small subset of these properties. And in fact, CP properties are key to the electroweak baryogenesis models. So why should we focus then on CP violating UCAVAs? Okay? So CP violating UCAVA is something that does not exist in the standard model. It is a coupling of the Higgs particle to fermions proportional to gamma 5. Okay? Now, from the phenomenological point of view, you can make the point that these are among the least constrained parameters that we have presently in this standard model. So it definitely makes sense to look for it because there's still room for large deviations. Okay? From the theory point of view, these type of couplings are precisely the ones that you need to do electroweak baryogenesis. So let me demonstrate this very pictorially. So electroweak baryogenesis happens in the following way. Well, the idea is that it could happen in the following way. So we need a baryon number violation. Perfect. We have it in the standard model because it's anomalous. We need CP violation, but more than in the standard model. So why not take the standard model and include a CP violating coupling? This is this operator here. It's a dimension 6 coupling that violates CP. And another thing that we need is we need to make sure that the electroweak phase transition is first order, so we can do this with another operator that changes the scalar potential of the theory. It is interesting that if you then just plug this into the numerics and try to get the correct photon baryon ratio, you get that the corresponding scales need to be roughly at the TV scale. So this is an indication that there's some hope that, you know, the LHC type experiments or TV scale experiments maybe have something to say about electroweak baryogenesis. So therefore, it is a sort of natural expectation in this sort of framework of electroweak baryogenesis to do expect that you have CP violation in the Higgs UCAVAs. And the question I'm going to ask is how we can look for a CP violation in all the Higgs UCAVAs, not just the top quark as in this toy model. So at the LHC, as I mentioned, we have a plethora of different experiments and different measurements. So these are the sort of kappa couplings, so they all need to be one, essentially, if the standard model is correct. And so we mainly have couplings to the gauge bosons and to third generation fermions, and only few information about the second generation fermions, so on muons essentially only. And we have essentially not much handle on the CP violation, right? So very weak constraints on the light fermion UCAVAs. The reason for this is that they couple proportional to the mass of the light fermions, so they're very small signals. So if you want to be sensitive to light UCAVAs, you would have to be very creative. So you would have to look at specific decays of the Higgs. We call them exclusive decays. And potentially, if you do things right, so you look something like at the Higgs going to some J psi and another photon, you can have sensitivity to light quark UCAVAs. You can try to do tagging, which is a limited mode charm. You can try to look at Higgs distributions and try to get a handle on the corresponding couplings. Even so, most of the time, we are very, very limited on the sensitivity to CP violation. Okay? And here comes the idea, and the idea is that are always CP violating, and these are the electric dipole moments, and they could actually, tell us something about the Higgs Yukawas. So, why should I focus then on flavor conserving? Because in a moment I'm going to talk about CP violating flavor diagonal Yukawas. So why should I focus on flavor conserving CP Yukawas? Well, typically CP violation is accompanied by flavor violation, okay? And flavor violation is very much constrained by so-called flavor changing neutral currents that I'm going to talk later. Even so, it is theoretically possible to have a new low energy sources of CP violation without flavor violation. Okay, so it requires some tuning or some mechanism like alignment. All right, and this is what I'm going to assume for this first part of the talk. But here I'm showing you why typically these signals are correlated to flavor violation. So CP violation and flavor violation typically are correlated. So these are bounds on assuming that the new physics is roughly at the 7 TeV, and this is the bound that you get on the coupling, and these are different flavor violating couplings in specific models that essentially they call Frogat-Nielsen models. They explain how to get the flavor hierarchies that we observe. Okay? So having said that, I will now focus on flavor diagonal ones, and I will ask the question, okay, so I'm not an experimentalist, so for me, I need to be able to combine within a specific framework, mathematically correct framework, all this information that the experiment is giving me. So here is where the effective field theories for Higgs come into play. Okay? So there are multiple around, but essentially there are two. Okay? So one is the so-called SMEF, okay? So which takes essentially the standard model as it's written and just assumes that the electroweak symmetry is broken linearly and extend this to dimension 6, 8, blah, 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 operators. Okay? This is fine. Okay? This assumes that the new physics scale is much above the electroweak scale, 1 TeV plus. Okay? Another possibility is the so-called HEFT, okay, Higgs effective field theory, which is essentially nothing more than chi-pt for QCD. Okay? So it allows also for a non-linear breaking of the electroweak symmetry. Okay? And then there is the kappa thing that appears in all the experimental plots in which kappa needs to be 1 for the standard model, and essentially this is, as I will show you, part of this. Okay, so SMEF and BSM Yukawas. So I want to have a coupling that changes the Higgs and the fermions. So I can write the dimension 6 operator. It looks like this. All right. In general, this coupling is a generic 3x3 matrix with complex entries. I can rewrite it in the broken phase. Okay, and I can make my UV assumption that there is some sort of alignment such that after I make this diagonalization, I have no flavor violation, but I do allow for CP violation. After I do this, I get essentially per fermion sector only 2 couplings, a CP even coupling and a CP odd coupling. Okay, and the corresponding Lagrangian has a very specific form in the following way. It predicts, in this dimension 6 SMEF story, it predicts that there is a CP conserving and violating coupling, and it predicts a sort of tower of interactions between the fermions and the Higgs. 1 Higgs, 2 Higgs, 3 Higgs. All right? So what we can do is we can use data to try to place constraints on both the CP even and the CP odd couplings that we have here. Right? Now, where is the departure to heft? Well, the departure is just these factors of 2, 3, and 1. In a more generic framework in which you do not, you allow for non-linear breaking of the electroweak symmetry, these parameters here, these numbers here, 2, 3, 1, are open. They can be whatever they want. Okay? This means, of course, that you have, you have a unitarity problem already at the electroweak scale, but that's fine. All right. Now, if the leading order effects are controlled, so if the leading numerical effects are controlled by the first term, right, it doesn't matter whether you work in heft or in smack. It's irrelevant. That's the case in what I'm going to present. Now let's combine this with a sort of kappa framework. Now it's clear. So the kappa framework that the experimental collaborations use, because it's so easy to just plot, is essentially just taking this Lagrangian, ignoring the terms that are not relevant for the experiment, and writing a kappa at the front. Okay, so this thing here is a kappa CP even, and this is a kappa CP odd. These are the two parameters. Okay? Good. Now, what are the LHC observables? So at the LHC, the Higgs is produced predominantly by gluon fusion. It decays predominantly to photons. There's also, production and decays over the W bosons, but I'm interested here in the effects that are proportional to modifications of the Yukawas. Okay, that's why I'm presenting these ones here. So what you see by looking at these things is, first of all, that there's not much sensitivity to CP violation, because in order to have an effect from CP violation, you need to be able to have an interference between this and other diagrams. So it's a loop-induced effect. And the total width is not a CP violating observable, so you have no sensitivity. And then you also have TT bar and CDT production that are relevant. Okay. So if you want to, perform a fit on your own, that's very simple, because there are open available tools with the likelihoods that you can take, and you can make the fits. Okay. Now, more interesting is, how do we get information for CP violation inside? And here comes the idea with the electric dipole moments. Electric dipole moments are CP violating observables and provide very stringent constraints on CP violation without flavor violation. Right? And what you should take out of this table is the difference between current and expected. Okay, so these are measurements of the electron EDM, the neutron EDM, and there are also mercury EDM and other atoms. And what you should take out of this is that there's order of magnitude improvements expected in the future. Okay. If you remember, maybe from some course in quantum field theory, the electric dipole moments, they are linearly proportional to the modification, whereas branching ratios are quadratically proportional to the modifications. This is good for us. Okay, it means that even if the new physics effect is very small, because I'm linearly sensitive to it, I can, I'm more sensitive than if I'm quadratic, like in these LHC observables here. All right. Good. Now, there's impressive improvements expected in the experimental frontier. There is progress in lattice QCD that is absolutely necessary to understand the theory predictions for this type of atomic and nuclear EDMs. And they provide indirect probes of low-scale CP violation in Higgs Yukawas. How is this the case? All right. So you take these. Yes, please.
The current is those which are achieved, right?
The what? The current is what achieved. Yeah.
This is what is already achieved.
Yes.
Okay.
And the expected are the projections. Okay. So order of magnitude improvement expected. Okay. So there's a very big experimental program behind it, and so data are going to come. So whatever I'm going to show you today, it means that I get a factor of 2 improvement in the future. Okay, so how does Higgs enter in these observables? So these you see here, it's electrons, here are neutrons, okay, mercury. So these are low energy stuff, okay? So electrons, and they emit some photon, and there's some CP violating thing inside. Well, it happens over loops, all right? So here are the so-called bar Z type diagrams, and I've written down the example of quark EDMs. So this is the quark EDM, so QQ and a photon, and there's some unknown loop that one needs to compute. There are W bosons and the Higgs, and here's my new source of CP violation, my CP violating Higgs Yukawa. Okay. Now, in the previous slide, I showed you that there's an electron EDM, but there's also neutron EDM. Okay. So I also have to include the chromoelectric dipole moment constraints, these type of things. And there's also something called the Weinberg operator, A Weinberg operator here, there's so many Weinberg operators, but this is the gluonic CP violating Weinberg operator, G tilde. Okay, and this operator also plays a role when I compute chromo dipole moments, electric dipole moments. Okay, so what's typically done is one focuses on one case, okay, and tries to place constraints. Okay. However, what I showed you before in the first slide is that for baryogenesis, it would be useful to have the constraints from all these Higgs U-kappas. All of them could play inside. Okay, so we need a global picture, and at the moment that you see a loop, you realize that potentially there must be some care. If we want to be precise, we may need to work hard. Okay, so let me make the point for precision. All right. So this is a loop. This is a Feynman diagram. We haven't seen many in this conference, but this is one of them. It's a two-loop one. Okay, and what you notice, these type of diagrams are called Barzilli. So what you notice is that there are two scales in this diagram. Okay, so there is the B quark scale and there is the Higgs scale. So if you would naively go and compute this diagram, okay, you would get a logarithm, and the logarithm is large. Okay, so the naive computation, if you do the estimate, is a bad approximation. It gives a factor of 5 uncertainty in the corresponding dipole moments, and the reason is precisely that we have a multi-scale problem. Okay, so if you want to increase the precision and understand precisely what type of bounds you get from electric dipole moments from something that is essentially happening at the high scale, you need to use the correct effective field theory framework, resum the logarithms, do the whole shebang. Okay, this is possible. In fact, often people assume that if you look at leptonic dipole moments, for instance, here is the electric dipole moment, these uncertainties associated to QCD are very small. But this is not entirely correct, because again, I have the same type of the same type of loop here, and again I get a large logarithm. And if I would just naively go and plug in numbers for MB, should I plug MB at the Higgs scale or should I plug MB at the low scale? You get a factor of 2 uncertainty. Okay, so also here, I will not demonstrate this because this is not so interesting for you, but again, if you want to have precision, you need to have the technology to resum all these logarithms. Okay? Now, having done so, one can collect all the predictions, okay, include all the Higgs bounds, and try to see what a combined fit of LHC and electric dipole moment data give us. Okay, and these are plots in which on the x-axis I have for different fermions. So here's the top, here's the bottom, here's the top. On the x-axis is the CP odd coupling, okay, CP violation, so it must be 0 in the standard model. And on the y-axis I have the CP even coupling, okay. Again, it needs to be 0 because this is the dimension 6 operator. So the standard model is always at 0, 0, 0, 0, 0, 0, okay. And there are different constraints. All right, so the different constraints are the different colors. Let's start with the LHC. So the LHC is blue. Okay, so for the top quark, it tells me that I need to be in here. Okay, for the bottom quark, there's a huge ambiguity. Essentially, I have to be in this circle. And now come electric dipole moment constraints, which probe only the CP violating part. So they probe essentially, there are like lines on vertical lines in these plots. Okay, so the electric dipole moment, very stringent constraint, essentially kills the ambiguity in the B sector. Okay, similar thing happening here for the tau, and for the top, we also have a strong constraints from the neutron EDM. Okay, so what this demonstrates is that there is a big complementarity between constraints from direct searches. Okay, so this is LHC, in which I directly produce my Higgs and I try to find its couplings, to indirect constraints coming from electric dipole moments in which the corresponding heavy particle, here the Higgs, is only virtually affecting the observable. Okay. Now, what you should notice out of this plot is also that the electron EDM constraint completely dominates over the quark EDMs. However, there's a caveat here, namely that this always assumes that the Higgs couples precisely to the electrons as we know from the standard model, which is also to be tested essentially. Now, if I zoom in into the top one, in the top sector, you see here there's the electron EDM constraint in green, and in blue the one from the LHC. And for baryogenesis, it is interesting to ask the question whether we can relax these very, very tight constraints. So this is 10 to the minus 2 on the top coupling. Okay, because if the coupling is so small, I cannot do electroweak baryogenesis just with the top. All right, and I will demonstrate by looking at this multi-fit results that with a global analysis in which more parameters flow, you can have cancellations. So essentially, this type of thing opens up the possibility for electroweak baryogenesis. So this is the same thing, but now I'm looking at the second generation. So I'm looking at charm quarks, strange quarks, and the muons. Okay, so again, the EDMs are always proportional to the fermion mass, and for the strange, the quark EDM is the main constraint. So this is the red one here, the neutron EDM. And yes, okay, so that's what I want to say here. And if I go to the first generation one, where essentially the LHC has not much to say apart from not saturating the total width, we see that the quark EDMs again play a very important role, much more than the electron EDMs that are typically used to make such studies. So I promised that I'm going to go beyond a single flavor. We went up to four different parameters, eight parameters actually. But here I will just show you one example in which we have a two-flavor survey. So we're profiling over the two parameters that are not plotted here. And we're looking at CP violation in the down sector and the up sector, and CP violation in the B sector and the, this is the strange one, right? The strange one. And what you should take out of this is that essentially there are no constraints from the LHC. Everything is coming from the EDMs. And even after I've included more and more parameters in my fit, I still have correlations. Okay? I still can constrain the parameter space. Okay? So this means that even though there are flat directions, okay, at some point I can still get bounds on these corresponding couplings. Okay? So the global picture requires precise measurements and predictions in multiple electric dipole moments precisely to disentangle and to stop these flat directions in my parameter space. So this brings me to the summary of the first example that I wanted to show. So flavor diagonal CP violating Higgs couplings provide a phenomenologically attractive setup. The low-scale new physics effects are still possible, and are excellent prospects, both from the EDM and also from the future LHC experiment to probe them. They are relevant for models of electroweak baryogenesis, and it's important to make the most out of this data to have accurate EFT computations in order, in light of this progress. So there are cancellations and correlations that can take place. So a global picture is required to understand this data. And so this was my first example about how there's a complementarity between high energy probes, and here I mean LHC, and low energy probes, here I mean EDMs. And now we're going to look at another one. Okay? So, yes, please.
Do you have an idea of what the more fundamental theory would be to produce these effective theory terms?
It is easy to produce these terms in the sense that if you add additional quarks and which have flavor violating couplings and you integrate them out, you will always get also these type of operators. The difficulty, big difficulty, is to make sure for the setup to have only CP violation and not flavor violation. So that's tricky. Okay, so therefore, for this type of cases, you will need alignment, flavor alignment. I will say something about it now. But typically, if you have alignment in flavor space to bring down flavor violation to observation, so that you're not excluded at the, let's say, 2 dB, typically you also have small CP violating effects. Okay, but this is a bit of a model-dependent question. Okay, and the bounds that I presented here hold also in the case of flavor violating couplings. Okay, it's just that if you have flavor violation, you need to also superimpose the flavor bounds. Yeah. Just out of my mind, right? If you just do a 2 Higgs doublet model, suddenly you have a lot of CP violating couplings. So if you take
CP violating.
Exactly, and if you integrate out this extra particle in order to get this, you get precisely this type of operators. It's just. Thank you for the question. Okay. So what did we do? So we went up here, and we looked at the Higgs, and now I'm going to try to go down here and ask the question whether current experiments, flavor experiments, since this is my expertise, have something to say about light particles, okay? Light new particles that we do not know whether they exist, okay? So since I'm here, I will have to probably tell you what the flavor changing neutral current is. So this is a process in which I change, let's say, a strange quark to a down quark, okay? They have the same charge, but they have a different flavor, okay? And these are important processes in current phenomenology, because in the Standard model they're always loop induced, okay? So we have a loop, and if you're careful and pick the right observable, you can also predict these observables very, very, very accurately. And because you can predict these observables very, very accurately, you have a chance of finding new phenomena, or finding new physics, if these new physics have new sources of flavor violation. I will go into this. So there is something called the flavor problem, which is that if you have heavy new physics, they can affect these flavor changing neutral currents, and therefore this new physics should be very high or have alignment. But there is also the possibility, which I will talk in the last 10 minutes, of having light new physics, in which case these flavor changing neutral currents could provide a possibility for a strange quark, for instance, to decay to a down quark and some light new physics. This could be axions, QCD axions, or dark photons, for instance, okay? Now, is flavor the answer to all? No, it is not, okay? So, experimental data have the potential to provide some answers. However, there are no guarantees. It could be that flavor violation in new physics is fully aligned to the Standard model, and then I do not see flavor violation beyond what I would see in the Standard model. Or it could be that my new physics is decoupled, is very heavy, and then all these effects are small. Okay? So it's an opportunity, not a guarantee. And therefore, there are two semi-orthogonal strategies. So one can expose the deviations by looking at precision and global fits, or one can try to go beyond established interpretations of data and observables. So here, I would like to make the point for light new physics, and let me give you the example that maybe you should remember more than what I'm going to tell you afterwards. The case of the QCD axion. So the QCD axion is a particle that solves a fine-tuning problem of the Standard model, namely the strong CP problem, dynamically, and it is a pseudo-Goldstone boson. Therefore, every coupling that I can write that is compatible with it being a pseudo-Goldstone boson is fine. So I can write a coupling of the QCD axion to a flavor violating coupling of the QCD axion. It's derivatively coupled because it's a Goldstone boson, and it's down by the so-called Peccei-Quinn breaking scale. Okay. Now, if I just do naive dimensional analysis for the rates of, for instance, K to pion and a QCD axion, or B and pi to a QCD axion, I have to divide by the total width, which is a weak width, so it goes with 1 over mw to the 4th. And therefore, what you see here is that the branching ratio is always inversely proportional to the Peccei-Quinn breaking scale, but has an enhancement proportional to mw to the 2 over mk, the meson mass, to the 2. So this shows that there is potential high sensitivity to light new physics if this coupling here exists. And this is demonstrated in this plot here, in which I have the mass of the QCD axion, or equivalently the Peccei-Quinn breaking scale, and what type of scales, kaons, or here are B mesons, or muons probe. And what you should take out of this plot is that, for instance, kaons already probe the window for QCD axion dark matter. So the QCD axion doesn't have to be dark matter, but it can be if you're roughly here. So what could light new physics be? Well, they could be scalars, like the QCD axion, or less motivated scenarios like axion-like particles. They could be fermions, like light sterile neutrinos, fermionic dark matter. They could be vectors. We already heard a little bit about dark photons, light Z primes. And the phenomenology at the particle level depends very strongly on their masses, the lifetimes, and the exact couplings that we have to the Standard Model. Okay? So the strategy that you must pursue to probe this type of light new physics can be very different. Okay? And let me demonstrate this in terms of the light vectors. So essentially, dark photons with flavor-violating couplings. So just as I did an EFT for my Higgs, I can essentially take my light dark vector and add flavor-violating interactions. I can do it in two ways. I can write a dimension 5 or a dipole type of interaction. It's fine. Or I can write a vector type interaction that is, however, protected by gauge invariance. That's why I wrote a mass of the B prime over lambda at the front. Okay. Now this is essentially model dependent. The power. That's a technicality. I can tell you more. And then one can ask the question: how can I probe this model independently? These couplings. Okay. So there are many different data that I can use, and the experiments are actually not performing yet this type of searches, or very few of them. So I need to probe for the different couplings, for the different sectors, the different couplings. All these bounds are going to depend on the mass of the vector, and I can look at two body decays of some particle to another particle and this light particle. For instance, pseudoscalar to pseudoscalar and dark photon, pseudoscalar to vector, or baryon and vector. So these are invisible signatures. And I have to do this if I want to probe all the couplings. Okay? So let me show you which are the observables. These are roughly the observables that one can use. And I will not bore you with the details. I will show you the results. Okay? So, no problem. So here's the example. Okay? So this is the probing the coupling of a B quark going to a strange quark. There are different lines. If you're above the line, you're fine, because this is the scale of new physics. Okay, so here's an excess. I can tell you later. So what should you take out of this plot? The first thing that you should take out of this plot is the order of magnitude of these scales. So flavor is essentially probing very high scales. So these couplings need to be very small in order to evade the current constraints. Okay? Another thing that you should take is that not all lines on the right and the left are there. Okay, so on the left is the coupling without gamma 5, and on the right is the coupling with gamma 5. And because of the parity invariance of QCD, the stringent constraints for pseudoscalar to pseudoscalar are absent on the right one. Okay, that's the type of things that you should take. What you should also see is that, of course, this bound depend very strongly on the kinematic endpoint, right? So they depend. If the mass of the vector is heavier than this decay, then you get no constraint from two body decays. Same thing you can do for the kaon sector. Here the constraints are even more stringent. This is 10 to the minus 7. Okay, and for the charm sector as well, where we would have to. The experiments do not provide this interpretation, so we'd have to recast and make some assumptions. That's why there's the dashed lines. And you can do the same also for the vector-like coupling that I wrote down, not the dipole one, and you get similarly strong constraints. So this brings me already to the summary of this part of the talk. So this is possible to hide new physics with light new physics, as long as the corresponding coupling is very small. QCD axions, sterile neutrinos, dark photons are viable and interesting, partly motivated candidates for such light new physics. And quark flavor can provide competitive tests if these couplings exist. Okay? So we would have to look for interpretations of invisible signatures. It's going to be an important part of the future program. So in terms of light-dark vectors, what I demonstrated is that there is an rich flavor phenomenology, and I considered different type of couplings and showed that there are multiple channels and dedicated analysis that need to be pursued to get a good idea about what's happening. And this brings me to my conclusions. So I talked about two different cases in which essentially new physics is probed at very different scales. So in the first case, I talked about how new physics is hiding in Higgs couplings in a way that is not consistent with the standard model, and how to connect Higgs physics to electric dipole moments. And in another example, I assume that the light new physics is there, but we don't see it because it's very quickly interacting with us. And therefore, I would like to end with the 2 points, so that even if heavy particles are experimentally not directly accessible, they can leave imprints in low energy observables. And since the LHC so far has not seen a new resonance, a new particle, maybe this is the way where the LHC program and the future experimental program at the high energy frontier would go. Okay, so you have to keep that in mind. And in all this business, the precision and the broad interpretation of data is essential in disentangling these small new physics effects.
Thank you, Manuel. Questions? Manuel.
Here I can say mine.
That's it. Question. I do have a question. Couple of things. Okay, let me ask you the following. So in the picture you show about the size of these couplings,
The light one?
the light ones, in the first, let's say, part of the talk, you can assume that the lambda is 1 PV. How sensitive all these, let me say, constraints are on the value of the lambda? So if you have lambda, let's say, 10 PV.
Right. So typically what people are going to tell you, this is just a scaling, but this is not entirely honest, because there is an RGE effect.
Right.
And we have taken this into account. The RGE effect is important in the nuclear EDMs, where these logarithms are playing an important role when you run from the Higgs scale down to the B scale. And we check that even if we change from 1 to 10 PV, they're not significantly different. Okay?
Not even an order, I mean,
not an order of magnitude.
Not an order of magnitude.
Not an order of magnitude.
Because you see, I thought that maybe it would be more convenient to use just one, let me say, new parameter for the gamma pipe coupling, not two, not C and lambda.
But that's not possible because of the effect of what you're saying. So the experimentalists will tell you, no, there's only C over lambda. But this is not true, because you fix your scale at lambda and then you need to run. So there are intrinsically two parameters. One is the naive one at the ball level, essentially, for C level, then it's C over lambda. But once you include RGE, you get a logarithm of the actual scale, not C.
And I have another question, very quick. Have you checked this with the old left data, which were precise because it was left of collider? We have some bulbs in these STU oblique parameters. And then these parameters are sensitive to new physics and also are sensitive for sure to a CP, let me say, evaluating coupling in the Higgs. Because your Higgs is the same, is the standard model Higgs. You see what I mean?
Yeah.
It's not a new particle.
Yeah. So, right. So, what did we do? So we included these dimension 6 flavor violating operators in order to get you're right. No, in order to get an effect in the STU parameters, the effect is a one loop effect in which these dimension 6 operators mix down to the HDH, the STU parameters. And we check that these are sublinear with respect to the EDM constraints, as long as the EDM constraints apply.
Questions? No? Thanks much. We are off by 20 minutes, so...
So when do we resume?
Huh?
When do we resume?
In in 20 minutes. Let's cut 10 minutes from the half an hour break.
Okay, in 20 minutes.
The next speaker is Konstantinos from Queen Mary, and he's going to tell us about deep high temperature boosters.
Thank you very much. Thank you, Yanni, for organizing this wonderful meeting. You know you're getting old when you realize that the last time you spoke at this conference was recently, and then you check the date, and it was in 2017. Yeah, ouch, I guess is what I should say here. But it's wonderful to be back. It's wonderful to witness all these wonderful talks. And today I'm going to be talking about this paper, Deep Finite Temperature Bootstrap, which appeared last August in collaboration with my wonderful colleague Vasilis Niarchos from the University of Crete, my excellent PhD student Mitchell Woolley, who is on the postdoc market this year. He's an excellent PhD student, and he's going to be a fantastic postdoc. And also Alex Stratoudakis, who was Vasilis' master student in Crete. Alex is applying for PhDs this year. He contributed very significantly to this paper, both in terms of analytic computations and also in terms of code writing. And to make things even more impressive, he's been holding down a job as an undergrad and master student as a firefighter full-time. So I hope that he's going to get something really, really good. Good, so I'm very lucky today because yesterday you heard a talk about finite temperature CFTs and by Tassos Petkou, and there was also a talk about Hamiltonian truncations by Spyros Soteriadis. And my talk is going to be involving the finite temperature CFT component, but also a component that has to do with truncation methods and how to go beyond them. So you've had some introduction to that. I'm going to be focusing on the bootstrap and some general words about the bootstrap philosophy, which comes from the early days of high energy physics. The main idea is that a theory has to satisfy certain consistency conditions, and then maybe these are enough to completely determine the physics. So this originates, as I said, from the old S-matrix program, where the idea was that analyticity, unitarity, and crossing would be enough to determine all observables for strong interactions. This did not come to pass. QCD came along as a better model for working with strong interactions, but a version of this idea is used to great effect today in the so-called modern conformal bootstrap. So I will be focusing on the conformal bootstrap. CFTs are ubiquitous. They govern the UV and IR behavior of quantum field theory. They appear in the study of critical phenomena and also quantum gravity via the ADS-CFT correspondence. But there are other applications of the bootstrap that you might encounter if you're not working on CFTs, such as the modern S-matrix bootstrap, the cosmological bootstrap, the quantum mechanical bootstrap, modular bootstrap for two-dimensional CFTs specifically, and so on. So what I will be thinking about today is CFTs in more than 2 dimensions. The motivation for this talk is the following, that from a sort of bird's eye viewpoint, the conformal bootstrap program aims to open up the way for non-perturbative solution of CFTs. And I will be particularly interested in the numerical implementation of the bootstrap, which has yielded very impressive results over the last 15 years, including the record determination of critical exponents for the 3D easing model. So broadly speaking, it relies on leveraging a collection of sum rules arising from the consistency conditions that appear in your problem. They look a little bit like this. There is a sum over the spins and scaling dimensions of the operators appearing in the spectrum of your theory, also sometimes some OP coefficients. There can be a vector of these sum rules because there's some dependence, some, let's say, complex parameter having to do in the zero temperature case for 4-point correlators with the dependence on the cross ratio plane and so on. I will make this explicit later on. There might be many of these conditions. And if you were trying to solve this thing head on, it would be a very hard problem to attack. There is a reason here. First, there is these sums are infinite, so they are non-compact sums. And also, these functions here depend non-linearly on the dimensions and sometimes the spins of the operators involved, and they are the optimization problem that you try to solve is non-convex. The workaround that came with the seminal paper of Bardazzi, Richkoff, Tony, and Vicky in 2008 was to sidestep this and map this problem to a different problem, where you apply a collection of linear functionals to this crossing equation, and you map this to one of a convex optimization problem that makes use of linear and semi-definite programming tools. There are many applications of this idea, again very successful, as I mentioned a second ago. There's packages such as SDPP, which stands for Semi-Definite Programming B by Simons Daphne in 2015, and there is hundreds of papers approaching the bootstrap in this way. But what I would like to talk about today is revisiting the direct or constructive solution to these crossing equations, or to these sum rules. And there are several reasons why you might want to do that. First of all, in this linear functional approach, one needs to make some assumptions about the spectrum of your theory, and maybe other approaches, such as the constructive approach, could explore the solution space and guide those rigorous approaches. So I'm not aiming to replace these rigorous approaches, I'm aiming to supplement them. Also, one would like to try and develop some more efficient numerics for the bootstrap. And finally, maybe the most important one is that the bootstrap approach that uses the linear functional method relies on the positivity of certain parameters in your bootstrap problem, which are there, for example, for a collection of theories at 0 temperature and the 4-point correlator bootstrap, but is not present in theories such as CFTs at finite temperature, theories with defects or boundaries, the bootstrap arising from 5-point correlation functions, and so on unitary theories, etc. So there's a large collection of CFTs where you need to try and attack the numerical problem in a slightly different way. So coming back to this direct approach, how can one attack a problem with an infinite number of unknowns? Up to now, there have been a couple of ways to try and do this. One is to truncate very hard, introduce some scale, some arbitrary conformal dimension, above which you just simply truncate the spectrum. And this was initially proposed by Yotzi in 2013, and for very special cases, it seems to give results which are relatively good. There's also soft truncations, where you try to model these contributions above the cutoff, which I will refer to as tails from now on. And we did that with something that we called effective operators in a paper from 2013 with Vasilis, where we looked at 1D CFTs arising on the infinite Wilson line in n equals 4 super Young-Mills. In the finite CFT case, there's also some attempts to put some bounds on the R dependence of the contributions to your crossing equations as delta goes to infinity using Tauberian theorems. This, once again, relies on some input about the spectrum of your theory. But what I would like to talk about today is something that goes beyond these truncation approaches. And because these are generally hard to control in terms of systematic error, so I would like to introduce a novel framework for capturing these unknowns using two ingredients. One is dispersion relations, and the other one is artificial neural networks. And this will not be dropping any terms. We will be keeping everything in these sums. I will showcase towards the end a numerical application in the context of thermal CFTs, which are dual to black holes in ADS, and where we'll be able to extract some data on the dual gravitational theory. Any questions about the motivation? Okay, so the main idea is the following. I will take again the sum rule that I showed at the very beginning.
So maybe the main like dispersion relations and neural networks, which guide you how to truncate, is that the main?
There will be no truncation.
There will be no truncation.
I will use them.
This is what I missed.
Exactly. So there will be no truncation. This slide will explain this hopefully, but stop me if it's not clear. So I take the original sum rule, and I split it into a high spin part, so operators that are above a spin J star, which is something that I specify. I call this high spin part of the sum rule, and this is going to be approximated through dispersion relations. Then there's going to be a corresponding low part of operators which have spin smaller or equal to this parameter J star. And the low spin part is in turn going to be split into another two parts. The first one is what I will call the sector with discrete data, low spin, low dimension part. So I will select a certain small number of operators with dimensions smaller than delta star that I will keep track of as discrete data in my optimization. And then the infinite sum of operators above this delta star, again at low spin, is what I will try to model using artificial neural networks. So there's going to be three components once again. High spin part approximated by dispersion relations in a way that I will make concrete later on. A discrete part that is low spin, low scaling dimension above these two cutoffs, and a low spin, high dimension part, which I will approximate using neural networks. So I emphasize that J star and delta star are arbitrary. It's up to me how I split this, how make this split. Keeping J star, for example, higher improves certain approximations that I will do. It makes other bits more difficult to control. Hopefully that will become clear later on. So since I'm talking about artificial neural networks and capturing this part here, let me just have a very, very quick overview of artificial neural networks and maybe the most popular architecture, which is multi-layer perceptrons or MLPs. These are functions from some kind of the functions of with a real input and a real output. You have various layers here. These dots here are called the neurons. They are connected in this particular architecture. This is a maximally connected MLP where every neuron is connected to every other neuron in the next layer. There is the input layer, the output layer, and then everything inside is called the hidden layer. And what happens is that you determine the value of the layer at the next L, as you see over here, by multiplying the value of the previous one by this matrix, which is called the weight matrix, and then shifting it potentially by some vector, which is called the bias vector. Then you feed all this through some function called an activation function, and what the artificial neural network does during training is to try and minimize a loss function that you specify by changing these parameters. Okay, so at the end, depending on your loss, so usually you have a collection of data, and you try to model this data by a function, do some kind of regression. So then you try to minimize for the points that you have, the difference between the data that you have and the function that is predicted by this neural network, and hopefully this also predicts the correct behavior of the function going beyond the data that you've supplied. Now here we're helped by the universal approximation theorem. So if these sigmas, these activation functions, are some nonlinear function, can be hyperbolic tangent and so on, the neural network can approximate any continuous function. So essentially you have a neural network which for you can approximate any nonlinear function subject to the determination of the loss that you provide to the system. And you can choose many different architectures. There is no real theory behind how you tune the neural network or how you construct the architecture to get what you want. There's a lot of trial and error in this approach. So how am I going to use this in my problem? I have here the low spin, high dimension piece that I would like to approximate using these neural networks. And specifically in the context of thermal CFTs, I will get terms that look like so. So there's going to be a piece that is independent of the scaling dimensions of my operators. It only depends on the spin. And then the piece that does depend on the scaling dimensions, I'm going to absorb the sum of the infinite set of operators into a function of one real variable, a j. There's one of these functions for each spin that I have below my arbitrary cutoff j star. I call these functions tail functions. Neural networks can approximate these functions very efficiently. And because we do not have data in this problem, in fact, we very rarely have data in theoretical physics, unlike what happens, for example, in an experiment. The loss function that we're trying to solve for is the crossing equation of the sum rule that I want to, that I had at the very, very beginning. So maybe amusingly for us, from the ML point of view, if you do not have data and you have some constraint that you're trying to solve for in your loss function, ML people call this a physics-informed neural network. I don't think there's any physics that inform this choice. It's just some constraint that people introduce. For short, these physics-informed neural networks are called PINs. This is the architecture that we use. It's a very simple architecture. This is the number of neurons that you have in the first layer. And then this is not a maximally connected multilinear perceptron, multilayer perceptron. It's one where you've got these branches of 32 neurons for each box that you see there. And essentially I have one of these sort of branches for each of these functions that I'm trying to determine. So if I have aj here running from 0 to 6, and we'll see later on that it runs over even j's, I would have 0, 2, 4, 6, I would have 4 functions and 4 branches. This is a very sparse architecture. There's only about 40,000 parameters that I'm trying to optimize for, which for modern optimization algorithms in neural networks is a piece of cake. It runs on a laptop in about half an hour, unlike conventional neural networks with millions of parameters, or LLMs where small models have billions of parameters and large ones have probably hundreds of billions of parameters. Okay. Question? Okay, so the summary so far is the following. I'm trying to find constructive solutions to sum rules for my bootstrap problem. I'm splitting the sum rule into three parts. A high spin part where the contributions are going to be approximated through dispersion relations. I have not spoken about this yet. And an optimization part where there is a low spin and low dimension contribution, which is a set of discrete data, and a low spin, high scaling dimension piece where these tails, this infinite sum of operators, is going to be approximated as a function by neural networks. We organize the search in terms of a semi-definite positive loss. This loss depends on the discrete data and the neural network parameters that I described in the previous slide. And we'd like to minimize that loss. So this loss is our crossing equation or some version thereof. It's up to us how we choose that. The simplest thing that you can do is to just look at the LP norm of the crossing vector. If P is 1, this is just the Euclidean norm of the crossing vector. But you can do more creative things. We'll have a more complicated loss, which I have in some of the backup slides. If you're really interested, is a geometric loss that kind of uses the angle between the components of the crossing vector appropriately. We call this the dot loss. This performs much better. I will show you a comparison between the results between these two. And
could you clarify a little bit what you mean the crossing vector? So
yeah, the crossing vector is simply this this thing here. So it's this equation.
So you say instead of having something equal to 0, it equals some value.
It is still 0. It's just I want to create some kind of scalar quantity. So I'm looking at the Euclidean norm, for example, of this collection. So here, let's say you are in the 4-point correlation correlation function bootstrap at 0 temperature. So you have a dependence of this thing on the cross ratio plane. So you can do various things. You can start taking derivatives of this equation, and you have like collection of derivatives. So you have many, many equations, and these are components of this crossing vector. So you'd like to scalarize that thing somehow to have a loss function that you can sort of make as small as possible. Or you can sample some region of this cross ratio plane by creating a grid around some point where the OP converges quite rapidly, etc.
Okay, so with vector you mean you either sample some values for the cross ratio, so you take derivatives. Yes.
And these are all components of what I call the crossing vector, and then you have to scalarize. Instead of having, you can solve that as a multi-objective optimization problem. You have, let's say, 60 equations to solve, or you can scalarize it in some particular way where, you sum the absolute values of each of these components, for example, or the squares taking the square root.
So there is some freedom in how you
absolutely, and it's crucial. In fact, absolutely, and that's also an art. The way that you choose the loss function can very significantly affect how well the optimization works. That's right. Yeah. Any other questions?
This J star is going to be created as a parameter?
It's a parameter that we can freely tune, and I'll show you in a slide how things change.
And use it to further minimize?
No, it's what we call what's called a hyperparameter. So this is a parameter that does not enter the optimization. You just choose it, and you see, for example, if your problem is behaving in a better way.
So J is an integer.
J is an integer, correct?
Okay. And do you take into account, extra information, like for example, for J equals 2 and delta equals you know the coefficient of the J for example?
You can do that. So it's up to you. So I'm setting a very general framework here. I will talk about thermal CFTs. We'll think about very specific theories. It's up to you to say, for example, do I supply some information as much as I can, and then try to extract things that I do not know. We'll see that in the towards the end.
But then can you also generalize to J not being integer,
I think that would be quite hard, because then you'd have kind of a continuum of these functions that you're trying to optimize, right? I think one of the strengths of this, of the way that we set it up, is that you have sort of integer J, so that you've got an integer number of functions that you're trying to approximate using this neural network. Otherwise, I wouldn't know how to do it. Okay. Great. So let's go to an application to make this concrete. Consider CFTs on RD-1 times S1 with radius beta. This is what we call thermal CFT. Beta is proportional to 1 over the temperature of the theory. And I want to consider a very sort of simple case of a thermal 2-point function for a real scalar position at x and 0 respectively. My 2-point function, which has no trivial information, because generically 1-point functions in thermal CFTs have non-zero expectation value, is parameterized by this g. You can use the symmetries of the theory to reduce the functional dependence of this correlator to two real parameters, sigma and tau, which is the Euclidean time, and you can combine them in this complex combination, Z and this complex conjugate Z bar. I'm in a Euclidean theory here. I can also rewrite things in terms of a radial variable in kind of polar coordinates and W, which is e to the I theta. Now, this theory, because of the thermal circle, has a periodicity when your x or your sigma, I guess, comes back to itself with a particular period, and the two-point function doesn't necessarily obey this periodicity, and you have to impose it by hand. This is what goes under the name of the Kubo-Martin-Schwinger KMS condition, and it was noticed by Elshok and Papadodimas in 2011 that this condition looks very much like the condition that you, the way that you can recast the 4-point correlation, the crossing equation arising from the 4-point bootstrap at zero temperature. So you would like if you write it in terms of these Z variables, the two-point function as a function of Z and Z bar should be the same as the two-point function with just the replacement of Z goes to 1 minus Z and Z bar goes to 1 minus Z bar. So this is it is a constraint on the data of our CFT. We can expand the two-point function using a thermal version of the operator product expansion. So this is what you get generically. In this case, you get the kind of analogs of conformal blocks, if you wish, some functions that do not depend, in this particular case, on anything except from the spin and the dimensionality of your theory. You get the factorized power function of R to some power that depends on the dimensions of the operators exchange under the OPE. And you've got a parameter here, which is some constant, which includes in it information about the thermal theory. So it is expressed in terms of this collection of quantities. This is the 3-point function coefficient between phi and O of the exchange operator under the OPE at zero temperature. This is the 2-point function coefficient, which sets a normalization for these operators, and then there are some constants. This is the thermal 1-point function, which is the datum we're trying to determine. So what the bootstrap does in this case is, assuming knowledge of the zero temperature data, so assuming that we've solved the theory at zero temperature and we know these 3-point function coefficients and the normalization of your operators and the dimensions, the KMS condition poses non-trivial constraints for these thermal 1-point functions. So now for us, the optimization, what can it tell you about? It can only tell you about this combination A of O, but if you know, obviously, F and C, you can extract information about B. Yes?
This alpha O in general is not positive there.
Second?
This alpha O is not positive there.
Correct. Exactly. So thank you for the question. So in fact, this is one of the reasons why the conventional linear functional bootstrap cannot attack these theories, because this positiveness is key in mapping into linear programming or semi-definite programming.
No, I just had a curiosity about connecting this dimensional theory a little bit. So if I look at your expansion there, two-dimensional theory, P2, so these are not there?
Yeah, so you have to find some appropriate generalization of these. So this expression is. Yeah.
Because I was looking for things somewhere, because in two-dimensional finite temperature is not in.
No, you need to rework this for Okay, great. So let's take this 2-point function and then apply the framework that I described at the beginning of the talk. So I would like to split that in terms of a high and low spin part to rewrite the 2-point function as follows. So the low spin, low scaling dimension part is exactly of the form that we had in the previous slide. This is how you'd express generically this 2-point function in terms of this thermal OP decomposition. Okay. These are the discrete data that I will try to use my optimization and determine. Then there is the low spin, high scaling dimension piece, where I have resummed all these contributions into these functions A that depend on delta star. Once again, delta star, G star are freely tunable. And these are the tail functions that I will treat as functions that my neural network is going to try to determine. And then there is a piece that corresponds to the high spin part of my 2-point function. And there is a little bit of theory behind it. For those who know how this comes about, you can rewrite. So you can use the so-called Euclidean inversion formula to rewrite the coefficients corresponding to the high spin part in terms of a spectral representation of your 2-point thermal 2-point function, and then you can analytically continue to Lorentzian signature and re-express those coefficients in terms of the discontinuity of, again, the full 2-point function multiplied by some kernel, which you can determine. So the important thing here is that obviously you might say, okay, are you trying to determine this, but then you also have this as an unknown, but the information that goes into the discontinuity is a much smaller subset of all the information that you need to determine the full 2-point function. This is going to be, I mean, there's a lot of details that I'm sweeping under the rug, but we can approximate this in a very controlled way. And in fact, as I'll show you in a minute, the higher J star is, the better this approximation of this discontinuity. The important thing to stress here is that delta star, J star, again, are freely tunable. I'm not sort of throwing anything away and just shifting it around. If I try to optimize now for, I would like to take this 2-point function and equate it with its version where the parameters here are 1 minus z and 1 minus z bar. This is my KMS condition. I have many tools available to me where I can optimize simultaneously for these tail functions and the discrete data using, for example, Python tools that are widely available. No exact terms, no terms have been dropped. This is an exact expression.
Can I continue the last question before asked about PDs? What about 1D, like quantum mechanics? Have you thought of applying it to quantum mechanics?
We have not thought about that yet. Yeah. But you can do many things.
Because people in thermal safety, they drop the angular part.
Right.
They have only one parameter,
right.
Tau.
Right.
Which is like the quantum mechanics. Which is basically like it's trying to expand in a kind of Lorentz expansion,
right.
function of one variable.
Yeah. I think things should simplify. Yeah. Right. I think things would simplify in that case significantly. In fact, I should maybe say that in the treatment that I'm talking about here, we are not doing any kind of, we're not reducing the dependence on, the space-time. There are many approaches to finite temperature CFTs where people take the zero spatial separation limit and they set, for example, x goes to 0. This is in the full x whatever. So, for example, the results of Pomoni that I spoke about earlier on, where they used Tauberian theorems, they work in the zero spatial separation. Okay, great. So let me calibrate this in a case where we know what the solution is. So I would like to think about generalized free fields. As a sort of example, let's work in 4 dimensions. Let's assume so generalized free fields are fields whose correlator is factorized. We know the exact solution for the thermal 2-point function in that case. Let's say of 2 scalars of dimension delta phi. It's you can obtain the result as this sum over images. And it turns out that because of the particularities of this theory, if you were to rewrite this thermal 2-point function in a thermal OPE decomposition, the only operators that are exchanged are those corresponding to double twist operators. So double twist operators are simply operators constructed of 2 phis where you sprinkle these with boxes or partial derivatives. This n here denotes the number of boxes. The j denotes the number of partial derivatives corresponding to giving this operator's spin. And because of Bose symmetry, the spin has to be even in that case. This is a corresponding scaling dimension of these operators. And here I've just rewritten the thermal OPE decomposition of exactly what I've said by specifying myself to the operators that appear there. This is the contribution of the identity. These are all the double twist contributions. But because I know the exact results, I can solve for my OPE, my thermal OPE coefficients, and I can get an explicit expression for this theory. So here I know everything. Why is this useful for me? Well, it's useful because I can use it to see how well my approximation performs. So I told you earlier on that I have 2 kinds of losses, one which we call the absolute loss, which is the Euclidean norm of my crossing vector, and a more geometric loss, which I call the dot loss. So here, the question that Joros was asking, you see a very big difference when you use a different loss. How will they? So here, what I would like to do is plug in the analytic data and see in my approximations how close do I get to satisfying this KMS condition exactly. So here I have 0 discrete data. I've tuned delta star so that there is no discrete data. I only have tails and the discontinuity. And you see, as I increase J star from 0 to 8, for example, I go from a loss here of 0.1 to 4 decimal points. This dot loss starts at 2 decimal points and goes to 10 to the minus 10. So choosing the right loss function is very important in how closely you can get to the right result. Here I show you an example where I have delta star a little bit higher and I can take care of one discrete datum. There is a particularity here which was going to be important later on. Here, the discrete datum I'm keeping track of corresponds to this particular linear combination of 2 double twist operators, because it so happens, this is the lowest one that is non-trivial, it so happens that if you plug in here n equals 1, j equals 2, or n equals 0 and j equals 2, the contribution from these Gegenbauer polynomials is identical. So the optimization algorithm cannot separate. It's not identical, there's a factor of 3, but it cannot separate the contributions from these coefficients. So you have to keep track of that in this particular combination. So I plug in all the data that I know analytically to determine my tail functions. I plug in, for example, 90 data or 100 data that I've determined from this equation over there. I sum over them, I have my tail functions, and then because of the way that I've defined my dot loss function, this thing comes out for free if I am to satisfy my crossing, my KMS condition. As I increase J star, the loss becomes very, very small, and you can see here compared to the expected analytic value, I get much, much, much closer as I increase this value. So the take-home message is that the approximation works well, and it improves systematically as J star increases. So this is by plugging in the exact analytic data. So now, yeah.
Just a simple technical question. In your previous slide, there are cases where the zeta function diverges. So in all cases, like in 3 dimensions, for value delta phi equals half, and j equals 0, this zeta 1. So diverges. Can you see this kind of divergences coming in your?
Maybe we chose for that particular reason, or maybe I didn't write it here, but you'll see it in the next slide. We chose this value specifically to avoid having integer or half integer scaling dimensions for these. But there are subtleties, obviously, that have to do with integer and half integer values of these operators.
You can predict them, because you're just
right. You can do many things. So.
And again, could you remind us the 2 different loss functions are?
Yes. You're asking me about the loss function, so let me go to the to the extra slides. So one of them is simply this, where p equals 1. This is the absolute loss, and then the dot loss is this particular combination. So you can write the crossing vector, for example, as this combination of data that you know and data that you're trying to determine. And then we wrote this Baroque expression where this is the this is the cosine between these 2 components. And then once you set these things to be parallel, the second term sets them to be equal in magnitude as well. So it's some particular choice that. Let me go back. Okay, so this is what happens if you plug in the analytic data. What happens now if you do not plug in the analytic data and you see how well the approximation does, and try to compare with the analytic data. So let's choose J star equals 6 in this particular case. From this slide, you could say that, oh, why don't you just put J star as high as possible, right? But then you have more functions over which you need to optimize, and that introduces issues with the optimization procedure. Delta phi is some random numbers that we don't encounter the problems that Tassos was talking about. And then let's see how well the process does. There is some stochasticity. There seems to be some complicated landscape of minima in my loss. There's many minima of similar loss, and for that reason we actually deployed many agents, many searches simultaneously, and we kept the ones with the best loss. We kept a collection of them, about 10 for example, and what you see here are the results where the deep blue line, if it is, you can see it, is the average, and then the band that is a lighter blue color is one standard deviation around that average. The serrated red line is the analytic result. So we have J star equals 6. There is 4 functions that I'm trying to determine, A0, A2, A4, A6. A0 does not do very well at all. A2 does a little bit better. A4, A6 do much better. So there seems to be here, interestingly, some kind of flat direction in the optimization landscape, whereas A0 and A2 are not really, you cannot sort of tell them apart very well. Here I'm plotting the contribution of these 2 functions to my crossing equation. If you sum them up and multiply them with the Gegenbaur polynomials, they do much, much, much better. So this is the like a kind of a section on the real z-axis. This is, for example, what happens on the whole z plane. But again, the losses are not very good. They are of the order, as you can see there, the best one is about 10%, and then it gets much, much worse. So it looks like the optimization protocol is finding it very difficult to determine between find the right solution. So what we did next is to supply 1 point only from the analytic result. So we supplied 1 point only, and in that case, actually the optimization protocol finds the solution exactly. This is what this combination should be like, and this is what it becomes. So just by giving one datum that maybe you can determine from other means, you can get losses which are of the order of 1%. So what does that tell us? It tells us that recovering the approximate correlator is not stable without additional inputs. By that I mean low losses and small standard deviations for the tails, but if you provide one anchor point, the solution is completely determined. On the contrary, if you were to provide an incorrect anchor point, the stability is destroyed. Here I'm showing you what happens to these functions if I give the wrong anchor point, the one that corresponds to some random number. There's very high standard deviations which are trying to squeeze themselves to the anchor point over here, and there's very, very high losses. So I'm going to use this in the last 4 minutes to as a guiding principle. Conjecturally, to see if I can determine something for theories which are of interest in holography. So let's use the stability argument, low losses and small standard deviations, to see if we can sort of guide our optimization to finding solutions for large CCFTs with a gravity dual in 4 dimensions. These theories are relatively close to the generalized free fields. In addition to the identity and the double twist operators, they have contributions from the stress tensor and multi-stress tensors. So these are their dimensions, these are their spins, and these are the corresponding thermal 1-point functions. Note in this case that there's theories with the same spectrum. We expect theories with the same spectrum, many of them. So the KMS condition can have an infinite number of solutions, because we know from the gravity side that can have an infinite number of high derivative theories. Yes?
Yeah, actually I was just talking about that, about unique solutions. Yeah.
They do not have to be unique. And in fact, one of the reasons that we, I think these truncation methods in this particular case do not, I think, are not very well motivated, is that if you truncate the problem to a finite number of terms, then the optimization becomes convex, and then you're forced to only have a unique solution. Whereas here, by keeping all the terms, in principle, you can have multiple solutions.
So I guess that's why when you put one constraint, you get better. That allows you to pick one solution.
Yeah, I mean, obviously, at one point, it can kind of pass through that one point and then do different things, as you see in this case. But if you provide the correct point, it actually determines the solution exactly. So, obviously, in this case, I do not know the solution. So I'll try something a little bit more creative. Okay, so in holography, what can we do? We can solve the free wave equation. So the dual version of this problem is solving the free wave equation on black brane backgrounds. This has been done by Fitzpatrick and Huang. The energy momentum data, so these guys over here, AT and AJK, can be determined from the asymptotics close to the boundary of ADS. And interestingly, there is some kind of universality for the lowest twist energy momentum multi-stress tensor subsets here. There's a type of data. The twist here is the difference between the scaling dimension and the spin of a given operator. So the operators with J is 2K are related to powers of 8T for the and this is independent of the theory that you're thinking about, which is an interesting observation. However, the double twist data are much harder to determine, and they require the full solution of this free wave equation in the bulk of ADS, and they are not known from the gravity side. So question for the bootstrap in this case, A, as Olaja was saying, can we detect multiple KMS solutions corresponding to different gravitational theories? Can we detect universality relations of this type, or can we recover the double twist data? What we went for in the paper is this version over here. And this is my last slide. So once again, we picked J star equals 6. Delta phi in this case is 1.5. We're working in 4 dimensions, and we optimize for this datum, which is corresponding to this double twist, the lowest non-trivial double twist operator in my theory. There is input that I have to put in the discontinuity. I didn't mention earlier on, I forgot that the discontinuity in the generalized free-field case only receives contributions from the identity, so it's completely determined. In this case, it receives contributions from the stress tensor and multi-stress tensors. These are powers of the stress tensor with spin 0, 2, 4, and so on, depending on how you contract the Lorentz indices, and we have from the gravitational calculation values for these thermal one-point functions that we can supply. So again, as Tassos was saying earlier on, if you have some information that you know from your theory, you can put it in and see how well you do. So this, to help the search, because here I don't know exactly what I'm going to get, we tried the following trick. We said we're going to start with a GFF solution because this theory is relatively close to GFF, and then allow for each of these tail functions some region where we're not penalizing the search to kind of look relatively close to GFF to see if we can find a low loss solution. This loss looks like this. This is just a formalization of what I just said. And playing with this parameter P to see how big this ball is around GFF. Originally, because if you restrict it close to GFF, which is not the right solution, it's going to give you high loss, non-stable solution with high standard deviation. Then you kind of expand enough for the optimizer to find the right solution, and then it kind of gets destroyed again. And we found that around P is 0.2, we got this result for this data. Now, I would like to compare this to the zero spatial separation results of Andrei Parnachev and his group at Trinity College Dublin in a paper that appeared on the same day. In the zero spatial separation limit, you can do more than we can do in this finite spatial separation case. They used about 40 energy momentum data, and they found a value for this particular thermal OP coefficient of 7.686. So our version is relatively close, but we have not optimized, our architectures, loss functions, etc. We have not supplied 40 data, we supplied only 7, etc. So this brings me to the end of the talk. Let me very, very quickly summarize. I described a new framework for directly bootstrapping without any truncations. I captured the higher priority dimension tails using neural networks, and I presented some examples of how this would work for the thermal bootstrap, but the method can be applied to other cases, including where positivity constraints are not available. Within finite T, unlike other approaches, we work at non-zero spatial separation throughout, and looking forward, we can obviously improve the optimization accuracy. What we did here was kind of proof of principle, incorporate more energy momentum data, make the discontinuities dynamical, get better double twist data predictions, hopefully holographic CFTs by performing certain improvements. We would also like to better understand this conjecture of trying to determine the solution by finding these islands of stability of low loss and small standard deviation, which was a conjectural guide for us to try and find some solution in the thermal CFT at high central charge. And finally, there's many things that one can do. Expand this thing to zero temperature theories, theories with deep expantories, high point bootstrap, etc. I'm a bit over time, but thank you very much.
Thank you for giving not only a very beautiful talk, but also trying to be on time. I really appreciate it, but I will then go the other direction. Since you had to rush through the example, maybe you could spend, I don't know, another 3 minutes on, describing in more detail. I mean, the holographic.
Yeah, very, very happy to do so. Yes. You're the organizer, so you're the boss. Tell me what you want to know. If you're one of the organizers.
So these are 4D correlators. Maybe you can.
So these are 2D correlators again in 4 dimensions. The 2.5 thermal correlators in 4 dimensions, and you'd like to find these data corresponding to these double twist guys, which you do not know holographically. Holographically, you have information about these guys over here and these guys over here. These data. It's quite difficult to extract them, but for low values, for example, of spin, you can do so, and you get, for example, expressions of this type of thermal data. However, for the double twist ones, you have to solve on the gravity side the free wave equation on the black-green background in the bulk, which is hard to do. And there, hopefully, the holographic calculation, the safety calculation can help. And this is a calculation, the one that I'm doing here, which is trying to predict the value for this datum, which is the lowest non-trivial double twist datum. And we got this figure using our approximation. So the only addition to the algorithm, maybe compared to what I did earlier on, is that because there's many solutions, and we saw in the generalized free field case that you can get results of this type which are not very good. And if you supplied one anchor point, you got a very good solution, you determined it. But here we do not know the solution. But because this theory is relatively close to GFF, it just has this stress tensor and multi-stress tensor additions. We start with say, okay, let my anchor point be GFF, and then start searching at some 10% away from this GFF position. Because GFF is the wrong solution. At the beginning, you get rubbish results. Then if you open it up a little bit more, but not to a crazy amount, it has the option of finding the correct solution. And then if you open it too much, there's too many possibilities of low loss, and then again it kind of goes haywire. So it's about opening this up, just right, so that it can explore but not too much, and it finds a solution which has small standard deviations and low loss. Conjecturally, for us, this is a criterion for selecting the right solution. This is what the value of this thermal one-point function coefficient is using this procedure. This is what Andre and company got using this zero spatial separation.
And when you say zero spatial separation, you mean x equals 0?
Correct.
Okay.
And in this case, you lose information about spin, so what you get for these, if you plug in, let's go back, if you plug in W inverse is 0, here you do not have, this thing becomes a constant. So you do not have any differentiation between different spins, so you get spin average quantities. Whereas in our case, generically, you can get information about these OP coefficients for specific spins.
But this particular coefficient is indifferent to spins, so that's why you can select.
So this particular coefficient is the same because of this accident that if you plug in delta whatever it was, if you plug in n equals 1, j equals 0, or n equals 0, j equals 2, the Gegenbauer polynomial gives you the same, or gives you something proportional.
Okay, so you in any case had some degeneracy, that's why you can check this combination.
Correct.
But that is the correct result, the 7 point something, because exactly it's, for this combination.
I think it's more accurate. I would say probably it's more accurate.
Okay, thank you very much.
So if we were to improve, again, I think what Andre and company did. I mean, they give a prediction for what this data is going to be. I mean, if we could agree with that by improving our optimization, that would be fantastic. You have two independent computations that lead to the same.
Fantastic. Thank you very much.
Should I assume that at zero temperature this theory becomes supersymmetric? The follow-up question is: if this is so, does it play any role indirectly?
No, I don't think so. In respect, so we have neglected. This is just a bottom-up theory where you just have scalars and the stress tensors. I don't think that if you had a supersymmetric theory that would come into the solution of the free wave equation in the Blackberry background. But you can consider more complicated theories. Maybe you can try and attack chemical phosphorylated fields, for example, with this approach, right? Finite temperature. I don't know.
Okay, two more questions and then we move to the next question.
Yeah. So on the holographic calculation, you say that this is close to GFF because
in terms of the spectrum.
Okay, GFF spectrum has higher spin field, where the holographic calculation actually doesn't have, as we know, higher spin field.
So here I have included only these double twist operators in my GFF theory. So these are.
Are you sure that holographically you see them, because holographically the calculation doesn't?
So I don't think for this thermal 2-point function do they enter? I don't think they enter in the.
Yeah, I'm not sure that they enter in the holographic calculation. That's how. I mean, I think the spectrum of the holographic 2-point function and the spectrum of the free or the perturbative 2-point function are rather different. The holographic one has only the energy momentum tensor, for example.
And these guys here, and these guys here, and this double twist data. considering a theory with a scalar.
Yeah, the building blocks, there are no kind of original building blocks like in Europe,
Right.
but the components are there.
Yeah, that's right.
In the sense of the components, I think, what he was saying that the figure that we just had.
Yeah.
Reality, of course, it's very
Right.
Okay, yes. I see what you mean, because the 4-point functions are not like
Mm-hmm.
the holographically they are not like that. The 2-point functions that compose yes.
Okay, the last question, yeah.
Sorry, just very quickly. Maybe you said it already, but this combination A10 plus 3A02, it looks like it's positive. Is there an underlying reason or it just happens that way?
It just happens that way. I do not know the underlying reason.
Okay, so I also have some more questions, but actually, so in the interest of time, let's move on to the next. Okay, so the last speaker of the morning session is Dimitrios Zoakos from the University of Patras, and he's going to tell us about holography and code-dimensional defect theories.
Okay, Yanni, thank you very much, and all the organizing team that is doing great work. Every year the conference is becoming better and better. That's my opinion. So I will tell you about recent work. It's not at all numerical, as we heard from Chris before. So I'm talking about holography of a codimensional artifact. It's a work that I've done with good friends and collaborators, Yorgos Georgiou and Yorgos Nardopoulos, and some work in progress. So let me start with a synopsis of the things that I will talk in the next 40 minutes. The first part is something like a motivation that basically it's going to be the state of the art and where my work stands for. So the second part, I will see what is the defect from the gravity side. It's a D5 brane, and I will discuss how the D5 brane is embedded in the geometry and how you avoid tachyonic instability by respecting the PF bound. Then after that I will have the geometry itself. I want to use it, and I will use it by doing two holographic computations. The first, the holographic computation of the 1-point function of the stress tensor, that background, and then the holographic computation of the current primary operator in this background. After that, I will switch gears and go to the field theory approach. I will try to present you the field theory dual of this defect theory. And in that, using the field theory solution, I will calculate the 1-point functions of these two operators at weak coupling. So the next step, natural step, is trying to compare the strong and weak coupling results, and I will show you what we find, and I will close with some conclusions in future direction. Okay, generically, the shift dynamics in the presence of defects describes a plethora of physical systems. For example, boundaries or interfaces to objects like Wilson loops or strings or branes. In our case, I will focus on the brane scenario. So in general, the defect breaks either partially or even completely the conformal symmetry of the ambient CFT. And in that way, the calculation becomes more involved. And that's where, if, for example, you are in qual 4, you have the gauge gravity duality in order to be able to perform computations, because you can go to the gravity side where you can do computations. So in general, the characteristics of the defect CFT are the following. If the defect preserves some amount of the supersymmetry, what are the boundary conditions that are associated with the defect that are integrable? I'm not going to touch this perspective in my talk. And finally, what is the codimension of the defect? The main focus in this talk is going to be of codimension 2 defects in the context of the gauge gravity duality. And I will tell you what I mean by that. So in the context of the ADS-CFT, the defects correspond to extended objects. Okay, in the bulk, for example, in our case, it's going to be a probe brane. that trap some proper internal submanifold inside the sphere, inside the ADS 5 versus 5. The characteristic example in this defect case is the D3-D5 frame intersection, which is a codimension 1. In that case, you have a defect in n equal 4 that from the field theory side is realized by a stack of D3 frames ending on the D5 frame and preserve some amount of the supersymmetry. And the holographic dual of that construction is a probe D5 that traps an ADS4 times S2. So NS2 from the sphere and an ADS4 inside the ADS5. So based on that, if you want to construct, like we want to construct a codimension 2 case, then the natural holographic dual should have a Gauss volume that contains at least an ADS3 factor, and then it should trap some internal cycles in the rest of the geometry. The presence of the ADS3 factor is what will encode the conformal symmetry of the defect. So that's the guiding principle in order to construct the defect solution. So in the case of the codimension 2 defects, the paradigmatic example is the Gukov-Witten defect that was calculated, that was presented several years ago. The holographic description of this defect is a probe D3 wrapping an ADS3 times S1. It is a supersymmetric defect, preserves half of the supersymmetry of the ambient space. And from the field theory side, you have some classical solutions for the fields with non-zero wave, diagonal waves for some of the scalar fields. Those waves exhibit a simple pole on the defect, which is the distance from the defect. And this is what gives you the space-time dependence that is dictated by conformal invariance. In the case of the codimension 2 defects, there is a very limited list of examples. And this is where our work is. You can put our work. Okay, so let me start with the gravity solution. As I told you, it's a D5 brane. The symmetry of the induced metric is ADS3 times S1 times S2, and it ends on a 2D submanifold of the boundary of ADS. That's why it's a codimension 2. Here on this table here, you can see the brane orientation. This is a standard D3, and then you see the D5 extends in these four directions, and it drops an internal cycle inside this cycle. So it depends on two parameters, and the bending assets is the one that I'm writing to here. I'm not giving you the method, it doesn't matter. It doesn't give any details. So these answers satisfies the equation of motion for the defect, D5 brane, if on top you switch on a gauge field of that form, where the parameter kappa that is related to the gauge field is related to the bending of the brane inside the ADS. So here, the functional form for the gauge field is dictated by the equation of motion for the gauge field, while when we satisfy the equation of motion for Z, it gives you this constraint that relates the parameter kappa with the parameter C. So as you can see, here is already a condition for sigma, so sigma cannot be larger than 2 square root. And of course, it's going to be greater than square root because of the relation here. So here I have depicted for you how the whole thing looks like. Here the green plane is the boundary of ADS. The vertical axis is the value of Z, is Z, and here I have depicted the boundary by suppressing X0 and X1, so it is only R and psi on the boundary. And of course, you cannot see the internal side. Okay? So the blue surface is how the brane looks like, and you can see it only touches the boundary of ADS at one point. That's why it's a codimension 2. And the orange surface that you see here is a limited case that it comes from respecting the Beer bound. So the blue surface, as I told you, is the brain, and then the orange is a limit. So as I told you, the brain intersects only at one point, the point 0 equal r equal 0. So that makes it a two-dimensional effect, a flat two-dimensional effect that extends along 2 of the 4 directions of the boundary. Of course, we apply the usual quantization condition that relates k with the number kappa or sigma, and in order to be more precise about what the effect looks like, you can see how the induced metric on the d5 plate looks like after a proper change of parameters. So you can see clearly here the S3 factor, you can see the S1, and you can see the S1. Okay, so in order to be sure that we have a solution that is stable, we want to examine the stability of the solution. This is ensured if the fluctuation of the transverse coordinates acquire masses that are above the BF bound. In our case, the BF bound is -1, and what we can say physically that from the point of view of the d5 brain, these fluctuations behave as scalars propagating in the distance. Okay? So naturally what you do, you introduce fluctuations around the d5 brain solution that I showed you before, and you expand both the gauge field and the transverse coordinate. So since we are interested in the time evolution of the fluctuations, we only, in order to detect possible tachyonic instabilities, we allow only dependence along the time coordinate. And after that, we move from the time coordinate to the proper time in order to be able to detect if tachyons appear in the geometry. So we arrive for the z to an equation of that form. So the mass is minus a square. So from analyzing that fluctuation, we put a stronger constraint on sigma than the constraint we found by solving the equation. So sigma now should be smaller than 1. And the value 1 is the one that you saw in the previous slide with this green cell.
Dimitri, so since you have assumed a lot of background knowledge, maybe so that everyone can follow, what is the BF bound?
The BF bound is given by supersymmetry, and if you are above this bound, even if the mass is negative, then the background has no tachyonic instability. If you are below, it has tachyonic instability. That's the situation. So the other equations for the other fluctuation modes, beta, tilde, gamma, tilde, and alpha, are trivially satisfied. Trivially satisfied means that you don't find any mass, the mass is equal to 0, and the other equation for psi tilde does not put any further constraints. So if we keep sigma smaller than 1, we are safe, at least for the BF bound. Okay, so now that I have in my hands the solution, let's try to do something, to extract some physics. So natural step is to try to calculate some one-point function of operators. An important observable is the web of the stress tensor. That's for us that was a motivation, because we know that from using conformal theory arguments, the web is 0 for a theory that has no defect or has a codimension 1 defect. There are calculations in the d5 case that they find it 0. So we wanted to construct a geometry with codimension 2 defect in order to be able to do the computation here. So, but also using conformal invariance constrains the space-time structure of the web of the stress tensor, and it has this behavior that you see here. So no cross terms. Me and nu here, they are directions on the defect. So here for us it's going to be 0 and 1, and ij are the coordinates that are orthogonal to the defect. Okay, and I and j are unit vectors normal to the defect. Yes, here I have. Yeah, so here, of course, I can choose the position of the operator the way it's better for me in order to have the simplest computations. Without loss of generality, I can choose the position of the operator at the boundary to be at that point. And after that, I can just so that relation here takes that form. So this is the relation, and all the information relating here. So this function H contains all the information, all the particularities of the specific defects here. So it depends on the coupling, and it depends on the number. So calculation, what I'm going to do is calculate it holographically using the tools of holography. And of course, now the recipe is almost known. I know that the stress tensor is dual to the fluctuations of the metric in that way. So the 1-point function of the stress tensor in the presence of a heavy object, in our case this heavy object is the DP brane, is given by the usual here. Okay? And at strong coupling, what we know is that the path integral that we see here is dominated by the classical solution. That's the standard law in order to be able to do this. This is classical. So, since it's dominated by a saddle point, this corresponds to the classical solution that we already have. So what I'm going to do is I'm going to substitute the classical solution in the path integral and try to get it. Very good. Of course, I have to expand the DP brane action that you see in the exponent here, and the first order term cancels the partition function that is in the denominator. So the final formula I have to use is this one here, where the stress tensor sits at the point on the boundary, specifically this point here, and the other point is the point on the brane. This is here, this is the defined brane, and this is the propagator. This is the graviton propagating between the two. Okay. Of course, after that you have to variate the brane with respect to the metric. That's a standard. That's a standard computer here. So now I have all the ingredients, and since I have all the ingredients, I can substitute everything in the expression I showed you in the previous slide, plus the classical solution for the defined brane that I had before, and the back-to-boundary propagator for the graviton. And after that, I have an integral. I have a 6-dimensional integral. The 6 dimensions are the dimensions on the brane, and I have to integrate them all in order to have an expression that depends only on the parameter x. After you do that, the final result is what you see in this yellow box, and the function, the strong coupling prediction for the function h, is what you see in this shape efficiency. Of course, the important thing is also that we get holographically what we should get by conformal invariance. So this is 1 minus r prime to the 4. Remember that the specific point that I put the operator on the boundary. So this is the strong coupling prediction for this function. Okay. And moving forward, I apply this. I will use again my solution in order to calculate the holographical.
For sigma between 0 and 1, that is supposed to be, is this monotonic, or the coefficient of 1?
True. We haven't plotted, to tell you the truth, because in the end, the only thing that we haven't plotted. That's the answer. In the end, we only take a very specific limit of that when sigma goes to 0. So we are not. We haven't thought about it. So the other holographic observable we would like to focus is the 1-point function of the chiral primary operator. Especially this 1-point function will be non-zero only when the chiral primary respects the SO3 times SO, the symmetry of the defect brane, and that means I have to choose, when we expand, we have to choose the specific spherical harmonic. We are not going to use all the spherical harmonics. The standard the standard procedure here is that we have to perturb the Euclidean axion with respect to the Sugra field that it is dual to the operator. This is the TBI part. I'm not going to give you technical details. This is the TBI part. This is the Vesumino part. These are H mu and A4 are the fluctuations of the metric and of the Ramon-Ramon form in terms of the Sugra field that it is dual to the current primary operator. And in that case, as before, the cartoon is similar to the previous one. You have the chiral primary located on the boundary, you have the brain, and you have to integrate, and the wavy line represents the fluctuations of the metric and of the form. That's the standard. And as before, you put everything in the DBI. This is just a very small technical equation about how the DBI looks like before any of the integrations. So here you see the supergravity field. This is kappa. This comes from the propagator, and then after that you have to substitute the value of sigma and start integrating again with respect to you have to integrate with respect to the coordinates of the brain. This is how the DBI term looks like. Again, this is what you would expect from conformal symmetry, and you have the strong coupling prediction. This is a number. This has to do with the spherical harmonic. This is a spherical harmonic that is related to the symmetry that I showed you before. Everything is in terms of delta, which is the conformal dimension, and sigma, which is the parameter that comes from the gravity side. And here there are some so psi1, psi2, and psi3 are expressions of delta and sigma, complicated, very complicated ones. And psi1, psi2, and psi3 are integrals that depend, that are expressed in terms of the associated Legendre polynomials. And in principle, these integrals you can do. You cannot do for a generic value of delta, but if you specify the value of delta, then you can do all of them for whatever value of delta you choose. And after that, you can calculate what is the DBI contribution for any value of delta. Of course, this is 50% of the work. After that, you have to do the same. We have to do the same for the Vesumino contribution. This is how the Vesumino contribution looks like. And at the end of the day, this is the result that you get after substituting the classical solution and integrating. Now, putting everything together, you end up with a strong coupling prediction for the chiral primary, and this is what you see here. So depends on, I have substituted the values of psi's, and the only thing that's missing here is the value of psi1, psi2, and psi3. So we can do the computation for delta equal 4. This is the final result. And it is straightforward to evaluate the result for the chiral primary for arbitrary large delta, whatever value we can do. So that finishes the computation for the gravity side, and going forward, switching gears, we go to the field theory approach and try to see what is the field theory dual of the gravity solution that I have presented just last ago. What would be the dual for the defined brain? So this is the Lagrangian of n equal 4. If you write down the equation for the bosonic fields, taking into account that the gauge field is 0, the gauge field from the field theory side, you end up with these equations. In principle, I would have some covariant derivative, but the covariant derivative becomes 0 because I have chosen the gauge field to be 0. So I have two equations, and if I assume that radial dependence for the scalar field, so the radial dependence from the defect, that's what I have here. So the second equation becomes the equation that you see here. So an ansatz, now an educated ansatz that solves the equations of motion, which will be the field theory dual for the defined brain, is the one that you see here. So 3 of the scalar, we put 3 of the scalars equal to 0, and for the other 3, this is the expression that we have. So here, you can see that the three of the scalars are 0 because for the answers that we took for the T5 brain, when you put this psi theta that probably you don't remember from my first slide, second, third slide, equal to 0 means that one of the S2s is going to 0, so there is no flux from that S2. So that one, so the S2 that has to do with beta tilde and gamma tilde is related to the scalars 5, 4, 5, and 6. Here you can see what you would expect from conformal symmetry, which is the presence of 1 over r prime, where r prime is the distance from the defect. And here you see that I have inserted the Pauli matrices, in principle, the k-dimensional representation of the Pauli matrix, where this kappa here is related to the flux that I have turned on from the gravity side. So these are the covenants that I just told you, summarized in that slide. And the final thing is that the symmetry of the brain is ADS3 times S1. The existence of this S1 that appears there is related to the angle of psi in the induced metric, and since there is this S1, we expect that the expectation value shouldn't depend on psi, and indeed doesn't depend on psi. Let me continue. Okay, so now that I have the solution, the field theory, same thing I did before, but now calculating the stress tensor and the chiral primary using the classical field theory solution. The relevant part of the stress tensor is what you see here. Scalars are done. I substitute the classical solution and I obtain the form that is dictated from a conformal invariance. And now the weak coupling prediction for the function that I showed you before is the one. So this is the complementary, if you want, result to the strong coupling result I showed you.
So what is K again?
K is the K that has to do with the gravity side, with the this is related to the to the quantization of the flux in the gravity side. So for the one-point function of the chiral primary operator at weak coupling, here.
But since Young Wilson is in the denominator too, how weak? How this is not well defined. So are you referring to T-Jam meeting small? That's what weak T-Jam means.
Yeah, it is a okay.
How is this in the denominator?
Probably has to do with the way I choose to write the I choose to put the kappa here. So.
Is it the 5 one or the equal 4?
Equal 4.
It's some kind of probe here on top of it.
It's a probe. It's a probe on n equal 4. Yeah.
But this young is coupling this young is coupling.
It's an equal 4.
Okay, but then the question is what?
Yeah, probably has to do with the way I wrote the. Here, I have used that relation here in order to insert the value of k, in order to write in gauge theory quantity. That's how the computation is going. So that's the weak coupling prediction for that. And okay, for the chiral primary, of course you have to respect the SO3 cross SO3 metric of the solution. And the more general chiral primary of n equal 4 that we can write is the one that you see here, where F's are the scalars of the theory, C is a tensor that are symmetric and traceless in the index I1 delta, and the normalization is chosen in such a way that the 2-point function takes the standard. So after that, what needs to be done is also to take the value of the spherical harmonics, the spherical harmonics of the S5 can be written in such a way when we introduce the components of the unit vector. And after that, I substitute the classical solution on the expression that I have here. And the final result is this one, where delta is equal to 2 lambda, and there is a unique SO3 cross SO3 symmetric chiral primary operator, and the expression is equal to 2. So this is the weak coupling prediction for the chiral primary operator.
The meaning of balancing at k equals 1?
Yeah. Yes. It vanishes. It's yeah. That's it goes to 0. These are limiting points. Also, that expression does not hold for delta equal to. Yeah, there are some points that they have to be treated with care. So, okay, I have a strong coupling result, I have a weak coupling result. In order for the DCFT to be valid, I should be able to find an agreement, at least in the leading term, in the expression of the weak and the strong coupling. And the limit that we are going to use in order to find an agreement between the two is the limit where this k over square root of lambda is much greater than 1. This will give us a non-trivial test of the correspondence, and similar agreement for the chiral primaries has been found in other codimension 1 SUSY scenarios, that is 3D5, and in the new SUSY scenarios of the 3D7. This situation of finding a limit where the two results agree is similar, is reminiscent of the BMN limit. So what you do in this case is you engineer a small quantity. Here, the small quantity is lambda over k squared. In the BMN limit is lambda over j squared, which are taken to be small at the weak and the strong coupling. You can expand in powers of this small parameter. Then one compares the observables order by order in the small quantity. If you do that, then the one-point function for the stress tensor in the limit that this parameter is very, very large, which means when sigma is 0, then the weak and the strong coupling results agree. Remember that I have that very strange expression for the H function at strong coupling. If you take the limit of sigma goes to 0, then the result that you get is exactly this one. As far as the one-point function for the chiral primary operators, expanding weak and strong coupling expression near sigma equals 0, we find agreement. For example, for the case of delta equals 4, I have the weak coupling prediction and the strong coupling prediction to be given by that. Okay? Here the Yakunis appears here.
So how much percentage do you have?
That defies very almost is a non-supersymmetric.
And you find that there is 2 agree?
Yes. But also here in the D3-D7 scenario, where also the D7 was a probe, they also found agreement between the two computations with strong coupling in a specific way. It's not there because of supersymmetry. Yes. So let me make some comments of that. There are some dots here and also some dots here that I haven't put. Dot means that subleading terms do not agree between the two scenarios. And there is one over sigma expansion between the expressions, and the subleading terms do not agree between weak and strong coupling. We have checked agreement for the leading terms up to delta equals 4, that works. And based on that agreement and the fact that I have the weak coupling result that I can easily say what is the leading contribution at sigma small, this is how the strong and weak coupling prediction of the one-point function looks like for generic value of delta. And not only for delta equal to 4 that I showed you. Let me comment that it is more or less natural that the agreement between strong and weak coupling is lost after some point. This also happens in the BMN limit. In the BMN limit happens after one or two loops. Here it is lost immediately. But this is something that is due to the order of limits problem that you take between weak and strong coupling. So it is natural to have something. So very good. So let me summarize. I present the new holographic duality of a non-SUSY defect CFT and its gravity dual. From the field theory side, it's a flat two-dimensional plane, either R1, or R2. From the gravity side, it's a D5 brane that depends on one parameter, since the other one depends on sigma, kappa depends on sigma. Rupture S2 carries scaling units of flux and has an induced metric symmetry of ATS3 times S1. We calculated holographically the one-point function of the stress tensor of the chiral primary. At weak coupling, we proposed the gravity dual and we computed also the one-point functions of the TU chiral primary, and at the appropriate limit we found agreement between them. That agreement provides strong evidence in favor of the duality. It means that we have constructed the correct, if you want, field theory dual. Before I close, let me tell you that in our case, the trace of the stress tensor is 0, which is related to the fact that both the space-time and the defect are flat. But generically, in a two-dimensional defect that is embedded in a d-dimensional space, there is a Weyl anomaly associated with the defect. And this is the general formula for that. So you have a B central charge that is related to the defect in the intrinsic scalar curvature, another one is related to the traceless part of the second fundamental form, and another one related to the pullback of the Weyl tensor to the defect. There is the value of D2 is related generally with the value of the one-point function of the stress tensor, and this is the relation between the two, where D is the number of dimensions, and of course at strong and weak coupling we found agreement for the D2, for this parameter D2, of the Weyl anomaly coefficient. And one of the future plans is to be able to calculate the remaining anomaly coefficients, B and D1 of the Weyl anomaly coefficient. And something that we have worked and we are in a good path is to include a new type of defective D5 brane that interpolates between the D3 and the D5 intersection. I have an extra slide if you want about that, but if you ask me, thank you very much.
So I have a couple. So the first is like, do you consider like bacteria versions of geometry?
In our case, no. Remember that in our case the physiology of the simulation is very difficult to find in bacteria geometry. The only scenario that people have done the calculation for a bacteria geometry is the case of the three dimensions. In that case, the bacteria geometry is related to some kind of bubbling geometry of Marcasena So in that scenario that they have the bacteria geometry, they are able to compute all these things for the bacteria geometry following the standard recipe. So they take the metric, they expand on the boundary, and they compute all the things. But in our case, that it's not possible, at least for now, to have a fully bacterial defined. I think this is the way out in order to be able to make progress in this direction. Yeah, but it is also probed. That one is also probed. It's not bacterial. But this is not bacterial. No, it's not bacterial. It's another probe that is. Well, no. When I say you take the D3 limit in the probe case, so the other D3 is going to be a probe, not the bacterial, not the bacterial. The bacterial version is.
the back-reacted versions are always the same.
I expect, but I don't have the full back-reacted solution. So I can do computations only at the probe level, not beyond the probe level.
Also, do you have any understanding, like, what protects the birds, like the one, for example, you said maybe it's related to the anomaly?
These are protected operators, both the current primary and the two. So as far as you...
But you said you don't expect it.
Yeah, but in the ambient CFT, in any quality doesn't matter. So if you stay away from the defect, these things are, this is the standard, they are protected. Also, so the conformal dimension is not, I'm not take corrections of the conformal dimension. Delta strong coupling or good coupling is exactly the same. I'm not correcting that.
Any other questions? Okay, so in that case, let's say we make it again. Okay, so I guess we can come back like at 2:30, for the afternoon session. So as a bit of the schedule.